So welcome back to this first session in the afternoon. Our first speaker is Marcin Marculewicz. You have 15 minutes, I'll give you a 2-minute warning.
Thank you. Thank you for the opportunity to present my recent work, and today I will focus on two unusual cases of the continuum reverberation mapping. And even though there are simple source or single sources, I would like to emphasize that LSST can do a great job on the follow-up of these interesting sources. So first of all, I would like to introduce and talk about the basis of my work. And I divided my presentation into papers, meaning that the X-ray weak quasar and lens quasars regarding the reverberation mapping of those two objects. So first of all, just briefly, it was said a lot of times yesterday, and basically we have the supermassive black hole, and we can imagine that there is a corona. The geometry is still under debate. Some people are saying it's low, maybe it's coupled with accretion disk, or maybe it's even a layer. So let's put aside that geometry is unknown and we are not sure what exactly we should care about, which geometry is right. Let's say it's an X-ray point source that basically illuminates the disk, and the radiation is absorbed and some fraction is reabsorbed in the UV and optical regime. So this is the regime I am mostly interested in. However, we can also do the reverberation mapping further out of the disk for the broadline region or a dusty torus. And there are many papers for the past years that basically trying to emphasize the discrepancy between the observations and theoretical approach. In this graph, I am showing you the wavelength to lag relation, where the points in color blue and red are the observations that we have, and the observations, or the fit to the observations, is in a solid line. In the dashed line, we can see the theoretical prediction that is based on the Shekura-Sunayev standard accretion disk model. It is said that it is called accretion disk size problem, where the theoretical approach is, or theoretical prediction is not matching quite well the observations. To test the X-ray reverberation, we wanted to check for one particular source, which is, it was X-ray weak on 2020. On this graph of the alpha OX to luminosity at 2500, it appeared X-ray weak. On the left-hand side, I am showing you the SDSS spectra, where we mark the G and R band responsive curves from the ZTFs to emphasize that those response curves are not contaminated by the emission lines, or there is some very weak contamination. So first of all, this is X-ray weak source and also weak emission line quasar. So how the X-ray processing can work there? Should we expect any variability in UV optical or not? We check the ZTF light curves, and the G band is in the green color, and the red color is the R band. We found that we can measure the lags. The cross-correlation coefficient is on the top panel, where the distribution of the lags is marked on the bottom panel. And when we found that the observed lag is around 32 days. Moreover, we wanted to test the relation that is basically driven by the diffuse continuum, meaning the luminosity to the radius at 5100. So it is said that the scaling relation is driven by the diffuse continuum, but how the weak emission line quasar can produce the diffuse continuum? We should expect that this source is not lying within the relation. However, as marked in a red color, our source is appearing that is lying within the relation. So we were a bit confused, but we were thinking that, okay, maybe the diffuse continuum is not the solid model or the solid physical explanation that we should consider to explain this relation. To summarize, the first source, we measured the time delay of 32 days. This is high redshift quasar, so it's also additional point that the reverberation mapping was done for not only local source that we were observing. Similar to others, time delay 3 times larger than standard accretion disk model. And we are postulating that two cases can occur regarding the exterior processing. If exterior processing is correct, maybe the geometry of the corona is, or the structure of the corona is basically anisotropic. Maybe there is some shielding gas, some inner part of the accretion disk that basically is preventing us to see the true power of the X-ray. And if the exterior processing is incorrect, we would emphasize that some models should be taken into the account more broadly. For example, magnetic couple for corona with accretion disk, or maybe some further reprocessor. Second reverberation was regarding the lens quasar. We can imagine that from our Earth or telescope, satellites, whatever you want to observe the source of your interest, we can have on our line of sight some stars, some galaxy that basically is bending the light that we want to observe the source. So in this example, we can see two bands or two different paths of the light, and basically we can see one source in two different images. However, this is not only the case. Depending on the alignment of the microlensing star or the microlensing source, we can observe up to few of them. This is example of 4 images where the brightness is changing from image to image. However, the reverberation mapping for the lens quasars wasn't successfully done for single image with different bands. So LSST for this case will be awesome to do that, because we can observe one image per source and also multiple bands. With ZTF, we were able to make, or that there was only available G and R band. I band is very little, therefore we only did the lag measurement between G and R bands for the Q on 0957 plus 561. On the top panel, I am showing again the cross correlation coefficient, and the time lags. The distribution is marked in the bottom panel, where the lags is around 15 days in observed frame. This source is also more than redshift 1 is exactly 1.41. So this is also nice to see that high redshift can be obtained regarding the reverberation mapping. We also added new spectroscopic epochs, which is important to, first of all, determine the black hole mass, and also the other parameters from the lensing, like the radius. So more epochs we have, the more constraints of the measurements can be done. Our black hole mass is aligning with the previous estimations, and also we try to, for the first time, measure the velocity propagation of the variability mechanism. To do that, we need to find the radius that is basically measured or based on the black hole mass and the luminosity. So if we are assuming that the standard Shakura-Sonaya disk is working, the assumption of the radius is biased by first of all, by the mass and by the bolometric luminosity. We know that the black hole mass can be up to 0.4 or 0.5 dex uncertainty. So the reliability of the estimation of the radius can be certainly biased. Therefore, we measure the radius from the microlensing observations. For this source, we have around 15 or 16 years of monitoring, so the half-red radius can be constrained pretty well. The measurement was done for the 5500, and to convert that to the ZTF measurement GNR, we have to transfer this measurement to the 5100 angstroms. So we have our radius, we want to measure the velocity, so we need to find what is the distance. The expected distance is basically the variability of the radius of G minus R, since we have only those two bands. And after simple conversion, we can measure the propagation velocity, which we found out is exceeding the speed of light, and the value is 1.7 of C. However, the uncertainty at least the upper error bar is a bit confusing, and also when we just say that the density is there, the propagation velocity is close to the speed of light. However, on the distribution, the bottom panel is the distribution of our measurements when the darker color, meaning more, the probability is higher on the darker color. The magenta line is V over C, V divided by C equals 1, when the dashed lines are indicated the 60, 16, 50, and 84 percentile of our measurements. To summarize the second project and also my talk, we measured the time delays for the lens quasars between GNR in one image. We also added new epochs and improved the black hole mass compared to others where the mass was calculated by the carbon-4. We also combined the half-Earth radius and measured the propagation velocity of the variability mechanism. We also emphasized that if the X-ray processing is not the solid model that we should consider, maybe other models have to be taken into account, and LSST will give us plenty of room to just test our models, whatever we want, whatever we like, or whatever physics we want to test. I'm leaving the QR codes if you would be interested in my work, and also I'm happy to talk. Thank you.
Any questions for Marcin?
Okay.
You should be able to hear you. Yeah.
So for your superluminal motion, does this take into account dilution when you're doing the calculation?
No.
Because I would expect, because your radius doesn't emit just a single wavelength, right? It emits continuum. And so that dilutes your signal, and expect them to effectively reduce the lag time that you see, which would then give you an exceedingly high velocity.
All right. Yeah, so no, we didn't take that into account.
Yeah.
So X-ray reprocessing is kind of the classic way to make Shigura Sunyayo disk vary, because they can't vary on these timescales. But in which case it's really key to look at the X-rays. So for those two quasars, did you have X-ray spectra?
For the lens quasar not, but for the X-ray weak, yes, and it varies between epochs. So yes. So your point will be that checking the X-rays and compare this with the light curve, right?
Yes, but also looking at the relative volumetric luminosity in the X-ray compared to the UV. Because many quasars have a UV that is dominant energetically, and so it doesn't really matter how much this varies. It's hard for it to make much variability in the disk.
So for the X-ray weak source, we found that the X-ray power is not enough to produce the variability in UV optical part. So we tested that, and in some cases it was like partial 15, and in the extreme was more than 100. So it was like yes, not enough.
Yeah.
Yeah, so for that sort of, I think what Chris may have been asking about was like contemporaneous X-ray coverage. I don't think there's contemporaneous X-ray coverage for when you were doing your.
The ZTF is catching that 2020.
Pardon me?
The ZTF is
So you have a catch,
yes,
oh, okay,
yes,
fine. You
yeah.
caught it in that.
Yes,
in the
yes,
weekday. Oh, good,
yes,
okay.
yes.
So then my question was, as we heard from earlier speaker, there have been arguments that, of course, the disk may be dominating rather than the diffuse BMR continuum. This is still a bit of a debated issue. If you look at your lag structure, do you see perhaps a short reverberation timescale associated with the disk, and then a longer timescale perhaps associated with any diffuse continuum, or?
In those cases, no. So
Okay.
for the lens quasar, there was study that they measured what is the impact of the broadline region, and it's below 30%. So we assume that it's not enough to impact the lags.
And for the weak line quasar, is it possible that you are seeing the disk in that case?
Yes,
Okay,
of course.
well,
Yeah,
okay.
yeah. And especially when we are taking that is high accretion quasars, when the inner shielding gas is preventing us to see X-ray.
Yeah.
So we should see the disk. Yeah.
Yeah, exactly. Yeah.
Yeah.
Okay, so we have the first online.
Should I?
Well, you can do it yourself, so yeah. What you can stop sharing.
Francisco.
I
You can just ask Francisco to speak and then.
Yeah,
Ah,
maybe
wow,
the speaker can unmute
Hi.
themselves.
Can you hear me?
Yes.
Oh, great. Yeah. Thanks a lot for the talk. It's a really nice talk, and I'm really glad to see that there are results for high redshift quasars. I have one question with respect to your first quasar, the one you were talking at the beginning. What is the variability amplitude are you getting in the light years? I think I missed it because you know those quasars, it's a luminous quasar, right? So the variability amplitude is quite small, right? So it's quite hard to get delays.
Yes, and I don't have the answer what is the amplitude, so I didn't test that actually. But yeah, you are right.
But you have light years, right? I mean, you show light years. Can I see quickly? I think I skipped this.
Yeah. So I should share again, right?
I see. Okay. Wow, this
Not significant.
really nice. I mean, you have really a lot of very nice features. Like, it's okay. Okay, thanks. That was my question. Thanks.
So if we don't have any more questions, we thank Martin again. So we move on to our next speaker who is online, Luiz, Matheus, Dourado, Sanches. Luiz, can you hear us?
Yes, can you hear me?
Yeah, perfectly good. So you have 15 minutes. I will give you a 2-minute warning. And just start sharing. Thank you.
Okay. Just a second. Mm. Okay. Good morning or good afternoon for you. Today I'll be presenting our work, Optical Variability Analysis of Low-Redshift Quasars with CTF and future prospects for LSST. So this study was developed in collaboration with Thaisa Stork-Bergman, Panda, and Igor Benat. So let's get started. First, we aim to investigate the photometric variability of quasars and how this variability is related to the physical and spectral properties of active galaxy nuclei within this redshift range here. Another objective is identify quasars that present a double-peaked profile in broadline region emission lines, and to explore if they show different variability patterns, amplitudes, or correlations with AGN properties. So this work uses ZTF data in preparation for LSST data. So to create our sample, we started with quasar catalog by like, and we also applied additional selection criteria to ensure higher data quality and reliability. For instance, we choose a signal noise ratio greater than 20 in the SSD spectra to guarantee good spectral quality. And to improve the reliability of the variability analysis, we only included quasars that were observed more than 100 nights in the ZTF survey. And this filtering step reduced our sample to 472 objectives. So from the sample, we visually inspected the SSD spectra to identify quasars with double-peaked profile, defining 3 subgroups: double-peaked, non-double-peaked, and an intermediate group. So the reason we separated the sample into double-peaked and non-double-peaked quasars was to test the hypothesis that double-peaked sources might show a stronger variability. This is because the double-peaked profile may trace gas that was more recently accreted into the disk and is located closer than to the central engine. So uh, we made the classification based on the shape of the emission line profile. Sources with clearly defined shoulders were classified as a double peaked. Those with less clear defined shoulders were labeled as intermediate sources, and sources with no shoulders were classified as non-double peaked, as you can see here. So to obtain the light curves, we use the forced photometry service provided by DZTF, and this allowed us to analyze the variability of the quasars in the G, R, and Y bands over a time scale of approximately 5 years. And this allows us to perform a short and long time scale variability analysis. But we only did a long time scale until now. So here we show examples of light curve with low, medium, and high variability. As you can see, the G and R bands provide good coverage over the full time range. However, the Y band has a significantly fewer data points. So since the G band had more data points overall and shows a higher variability, we choose to use it as a baseline for our analysis of variability. So the F-var of all our samples will be the F-var from the G band. So here in this slide, we show how much the emission lines contribute to the total. So in this slide, we show how much the emission lines contribute to the total flux in each photometric band. Overall, we found that the contribution is very small, and even in case where there is some contribution from the emission lines, it's not enough to significantly affect the observed variability. For example, um, even if an emission line contributes around 10% of the total flux, any variability in that emission lines would only affect a small fraction of this 10%, which is insignificant compared to the variability caused by the accretion disk. So the emission lines will not influence in our analysis. So in terms of methodology, we first obtain the light curves using forced photometry data from the ZTF with Muriel code. And to quantify the variability, we calculate the FR parameter, which is commonly used to measure the variation of amplitude in sources, and the equation is here. And to explore how FVAR relates to the AGN properties, we used additional data from the Wuhan chain catalog and like catalog. So here we show some of our results. According to the UN chain catalog, we observed that double-peaked quasars tend to have a higher black hole masses and stronger O3 forbidden line luminosity compared to the other groups. However, the bolometric luminosity appears to be similar across all the types, and it reflects too in the Eddington ratio too. We have a higher Eddington ratio for non-double peaked sources. But it's important to highlight that black hole masses here in the catalog are estimated using line widths. And since double peaked profiles naturally broaden the emission lines, this leads to overestimate mass values for these sources. Because of this overestimation, we later decided to explore an alternative method to estimate black hole masses and redo the analysis with more accurate values. So in this slide, we compare other properties of the sample. We find that double peaked sources show a higher variability overall. And they also tend to have lower full width for values for the forbidden O3 emission line and lower equivalent width of optical ion 2. And we will discuss the possible implications of these results later in the conclusion, what it means. So here we show the correlation between FVAR and AGN properties. We performed the analysis separately for each of the 3 subsamples, as well for the full sample. So we found that correlations are stronger when we look at the full sample. And in this case, the correlation with black hole mass is weak, while the correlations with Eddington ratio and bolometric luminosity are moderated. Here, and here. And with the O3 forbidden line and luminosity, we don't find any correlation. We show the results of additional correlations tests. And here, the only significant correlation we found was this one here, between FVAR and equivalent width of the MG2 line. And for the broad line region emission lines, we did not find any significant correlation. So neither for 8 beta or MG2. So we did other analysis. In this part of the analysis, we applied a power law fit to the continuum and calculate the spectral slope in this range here of wavelengths. And we could conclude that quasars with a steeper spectral slope tend to be more variable. Not too much, but it's a trend. And here, as I've said before, represents an alternative method for estimating black hole masses based on the work by Igor Benatti here. In this approach, we use the observed relation between FVAR and Eddington ratio to infer a new estimate for the black hole masses using these equations here. Here is the relation of Igor Benatti, and here is how we calculate the mass after this. So using this updated mass calculation, we find a moderate correlation between FVAR and black hole masses of the quasars. And we also observe that using this method, the masses become similar across all the 3 subsamples, not separating them. So to summarize our conclusion, the black hole masses from the Wu and Shen catalog are higher for double peaked and intermediate sources, However, the bolometric luminosity is similar across all three subgroups, which results in a separation among the groups in Eddington ratio 2. And as I already mentioned, these mass estimates are overestimated for double-peaked and intermediate sources, since the double-peaked effect broadens the emission lines. So this broadening reflects not only the gravitational potential, but also is sensitive to the inclination and recent accretion events. So we found all other trends suggesting that non-double-peaked sources are viewed more face-on, while double-peaked are seen more edge-on. So we conclude that the catalog masses are overestimated for double-peaked intermediate sources, making their Eddington ratios I don't know how to say this, unreliable too. So to address this, we used the relation between Eddington ratio and FFR from Benatti, and to obtain more reliable black hole masses. And finally, with this new estimate of black hole masses, we find a moderate correlation with FVAR for any subsample considered. So we also tested the hypothesis that double-peaked quasars are more variable, and this was confirmed. We observed an anticorrelation between bolometric luminosity and FVAR, which is consistent across all the three subsamples. The strongest correlation with FVAR was found for the equivalent width of the MG2 emission line, and this is likely related to the behavior of the bolometric luminosity. So as L ball increases, the continuum becomes stronger, which naturally leads to a lower equivalent width for the emission lines. So, and to finish, we also found that quasars with a steeper spectral slope tend to be more variable. So the relationships we found involving FVAR will be especially useful for the future studies of AGN variability with LSST. Yeah, I don't even need to say, but LSST will allow studies with much higher precision and confidence than ZTF, for example. So I would like to thank the Department of Astronomy at Universidade Federal do Rio Grande do Sul for their support. I would like to thank CAPS for the funding. And so that's it. If anyone has any questions, I'd be happy to answer. So
Thank you. So, we are Chris.
I don't need a mic.
No, we don't.
So, there are differences in line profiles, but in your model, what's the reason for those differences in line profiles in the first place?
inline profiles here. That's
So if we take the original masses, then the double peaks are at higher mass, so low Eddington fraction. And I think they're the ones that are most likely to be at low Eddington, maybe below the changing state transition. And so we're seeing much more X-ray view processing, which is boosting the FR. Yeah. And
Sorry,
then they have line profile because they are intrinsically a bit different.
sorry, I couldn't understand the last part. Can you repeat, please?
So if we believe the masses, then they are larger mass, and so lower Eddington fraction, possibly below the changing state transition. And so we get, they have a hard X-ray spectrum, and that dominates the bolometric. So FR is a larger fraction of reprocessed, so they have larger FR.
So this was the first thing that I think when I see this. But talking with the Thaisa, we could conclude that this estimating here, are or superestimated for double peaked sources and uh, subestimated for non-double peaked source. So this way to calculate mass with line widths is not uh, it's not a good way to estimate mass for double peaked quasars. So this mass estimation here, I think we could not use because it is uh, it's it's wrong for double peaked quasars. So that's why we choose another method to estimate mass. Let's here. And even this method have some issues. So to do this analysis with FVAR and black hole masses, I think we should try other methods to estimate the black hole masses. Analyze all sets or analyze all the geometry of the quasar. I don't know, we need to think about this. But until now, for double peaked quasars, we don't have a very good mass estimation.
I agree.
There was another question, Matthew?
So, Charlotte Ward did this analysis of 250 double peak emitters with ZTF data and found from power spectrum analysis that the amplitude of variability was pretty much the same between control and double peak emitters. The only difference on the variability was actually that double peak emitters tend to show a slightly longer characteristic time scale. So that would seem to be at odds with your finding that the amplitude of variability in the excess variance is more. The other point is you're finding a correlation with MG2 with equivalent width, which is surprising because AGN breathing, which is that correlation, that anti-correlation between equivalent width and line luminosity, is seen for H beta, but for MG2, the latest results seem to suggest that there's no correlation. And then for carbon 4 and carbon 3, you should see anti-correlation because of where those line profile regions are relative. But I'm wondering with double peak emitters whether you're seeing different emission coming from the MG2 structure, and that's maybe causing the result you're seeing, which is different from what's seen in the literature.
We also find the correlation for MG2, equivalent width of MG2 and the other H beta and MG2 and H alpha. But the stronger that we find, only the strong enough, was MG2, and I don't know why. I just can explain how equivalent width increases when volumetric luminosity decreases. But
Yeah, that's expected for the Balmer lines, but it's not expected for MG2. So it would be interesting if you had a control sample of non-double peak emitters, whether you saw the same.
so that's what I'm talking. I don't know why this happens. I
But you don't have a control sample.
What?
You have a control sample of non-double peak emitters in the same wavelength range, in the same redshift range, rather.
Yes, I have here is non-double peaked sample. I have the intermediate, and I have the double peaked sample, and I have this total sample here.
Yes,
And
that's what's in the literature.
yeah, sorry, I could understand. Sorry?
So there are recent papers which show you should only see this effect in Balmer lines, not in MG2, because the broad line region that's producing MG2 is further out from the central source, and so therefore it shouldn't see this effect so much.
So I'm wondering why you're seeing the reverse result, that you've got a stronger effect in MG2, but not in the Balmer ones.
Ah, okay. I don't know, but I could talk with Thaisa, Panda, and with you if you want.
Yeah.
So we could discuss this, why this happens, and what is the cause.
Yeah, I
So
think
if
online this discussion because we are on time and there are several questions actually for you, Luiz. So there's a Slack channel for this, and please post your questions there so that we can move on to our next speaker. Luiz, Ian.
Oi?
Ian, let's thank Luiz again. So our next speaker is Ian Davis.
o meu
And I should
quadro de...
Yes, I'm not pushing out. Oh, this one. I'll keep it on you. Oh, there we go. It's all the screens. I want to open position with this. Yeah, I want to just open. Oh. So. Sweet. Okay.
All right, hello, I'm Eden, and I'm gonna be talking about our simulations, on black hole binary systems, so that we can hopefully kind of find them in LSST's data. So our motivation for doing this is first that our previous, equipment hasn't had the ability to detect these systems, mainly because they lack either one of the three qualities of high resolution, high cadence, and long baseline. So a lot of them just don't have the ability to kind of observe these systems in the way that we need to observe them to confirm whether we're looking at a binary or just a single AGN. So because of that, we have no confirmed detections of binary systems. We have candidates, but nothing that we can sufficiently say is definitely a binary system. So with LSST, we're hoping to be able to observe periodicity in quasar emission, because that's our kind of biggest signpost for seeing a binary. And being able to observe these signals will let us constrain binary evolution and the different dynamical processes that are going on during the pre-merger phase of the binary system's lifetime. And that'll help us improve models and hopefully kind of keep understanding these systems better and better. And then since we're kind of at the forefront of gravitational wave astrophysics, these electromagnetic observations will let us kind of identify candidate systems that we can give to the gravitational wave detectors so that they know where to target. So things like LISA that'll be coming online in the next decade or so, we'll be able to target those candidates that we've identified from the LSST data. And be able to observe those in spiral and merger phases of the binary system. Okay, so the picture we're looking at when we're thinking of the binary is over here. And so we expect these to happen during galaxy mergers, when the two black holes in the center of the galaxies start kind of locking onto each other and orbiting each other. They're going to start accreting all of the surrounding gas that's around them and clear out this cavity, which you can see in the center there. And then since the black holes will still be accreting, they'll start sucking in material from the kind of donut-shaped gas that's still there. And that will form those blue mini disks that are bound to the black holes and will be moving with them as they're orbiting each other. And because the material in those mini disks will be not only orbiting the black hole as they're accreting, but then orbiting with the black hole throughout the black hole's orbit, they end up moving at speeds up to a couple percent the speed of light. So they'll have relativistic speeds where we'll see some Doppler boosting, which I'll get to in the next few slides. And then since we still have this open cavity here, as the black holes are moving closer to or further from that edge, kind of where this orange boundary is, the mass accretion rate onto the black holes will be varying as they orbit, because they'll be getting closer to the center here where there's not as much gas, and then closer to the edge there where they're closer to the gas. So the mechanisms for the periodic emission from the binary systems are first the orbital Doppler boosting, which I touched on in the last slide, which is from those mini disks being either redshifted or blue shifted, depending on whether they're moving towards us or away from us along our line of sight. And that's what gives us kind of a sinusoidal or modified sinusoidal shape in the emission, where it's going to be getting brighter when the black hole is moving towards us, and then dimmer when it's moving away from us. And then the next thing we look at is the gravitational lensing effect. And that's from when the black holes are kind of aligned with each other relative to our line of sight. The light from the black hole that's further back will be lensed by its companion towards us and give us these sharp peaks in emission when that light's being lensed towards us. And then the last signal we look at is from accretion modulation. So like I was saying in the last slide, when the black holes are moving closer to or further from the edge of that disk, they're going to be accreting mass at different rates. And so that will lead to them getting brighter or dimmer as they're accreting more or accreting less. So some of the previous searches have mainly focused on sinusoidal periodicity. And if you remember from the graphs I just had up, they weren't necessarily all particularly sinusoidal shaped. So two of the candidates we've been looking at with this are first PG1302, which has a sinusoidal shape. And you can see up there, we kind of aligned it with the Doppler boosting model, where again, it has this nice even sinusoidal shape because it's predicted to be a circular binary. And then spiky is our non-sinusoidal periodicity candidate, and that aligns with our model for the Doppler boosting with the lensing flare in combination. So the Doppler boosting gives it this kind of sawtoothed, jagged shape, and the main reason that's different from PG1302 up there is because spiky has a much more eccentric orbit. So we get this modified sinusoid, and then the spikes you can see there kind of in the light green are from the lensing flares. So our goal is to simulate both the sinusoidal and non-sinusoidal signals and kind of create this big data set for a bunch of different binary parameters and be able to use that to identify binary signals in LSST data. So the first step to constructing our model to simulate with is first to inject the periodic signal. So with that, we use Binlight, which is a publicly available code package, and that simulates the 3 signals that we're looking at and kind of allows us to plug in different binary parameters to kind of tweak those and simulate different systems. And the code, as it was originally released, only simulated equal mass binary systems. But with help from Magda Swick, we've used her accretion simulation data to kind of include non-equal mass binary systems in these simulations. And then the next step is to add the noise to these signals. So we use EasyTau, which is also publicly available, and that simulates noise as a karma process, which stands for continuous autoregressive moving average. So there's kind of a different order to the autoregressiveness and the moving averageness. And so that gives us things like the damp random walk, damp harmonic oscillator, and higher order things like that. And so that's what we'll use to model the stochastic variability from the quasar to kind of give us a more realistic picture of what we're going to be observing. And the inputs for that code are things like the variability time scale and the amplitude and stuff like that. When we get to higher order models, there's a damping time scale to include, and we define those using things like the binary mass, the average magnitude, and the emitted wavelength. And then the last step is to add the photometry and the observing cadences that LSST will be using. So for that, we use the Rubin sim package, which kind of contains all of the information that's up to date with what Rubin's planning to do for these observations. And so that will simulate our photometric errors and give us error bars onto our data points in the light curve. And for that, we're using equations 4 and 5 in Zelko's paper, and then also got some help from Jesse Renaud and Colin Davieri in order to kind of work those equations into the code for us. And then it also gives us the cadences for the wide, fast, deep, and deep drilling fields based on the particular position on the sky that we're looking at. And so that'll give us these gaps in our light curve that align with what LSST would be having when it's observing a particular location on the sky. So here's our parameter space. We keep it pretty broad and uniform to kind of go in there blind and not kind of add any bias to what we're simulating, so that we have this large range of simulations that can kind of be adapted to whatever systems we're looking at. And because we have such a large parameter space, we kind of check and make sure that the simulation will be bright enough for LSST to actually observe before we run the simulation. So we have it checked and make sure that in all 6 bands, there will be at least one band where the binary will be bright enough to observe. And if it's not, then we just kind of reject that and find a new set of parameters and make sure that's bright enough, and just kind of keep looping through that to find parameters that are going to be bright enough to actually observe. And then some of the other parameters we looked at were Eddington fraction, which we selected based on total mass, and then the spectral slope, which we determined based on the emitted wavelength. So we overall are going to do 4 data sets total, which will each have 600,000 simulations. The first 2 data sets will be the signal plus noise model, which is the periodic signal with the either damp random walk noise or higher order karma model noise. So that would be things like damp harmonic oscillator or the higher order than that. So that'll give us 2 different data sets depending on which Quasar noise model happens to align better with our data. And then we'll be doing noise only simulations that just have the damp random walk or higher order karma model noise kind of centered around an average magnitude to give us a like null case to compare to when we're trying to see if we're properly identifying periodic signals in LSST data or just seeing noise that looks periodic. So we split each of those groups of 600,000 simulations into 3 groups based on period. So we have our short period, which is 1 day to half a year, and then our medium period, which is half a year to 2 years, and then long period, which is 2 to 10 years. So we cut it off at 10 years so that we'll be able to observe at least 1 period from this binary system. And we split it evenly just to kind of give us an equal range of each, again, to kind of go into this blind and not accidentally cut off some of the binary systems we might be observing. And then each of those period groups will separate into 90% wide, fast, deep field and 10% deep drilling field. So that'll give us simulations with both of the 2 different observing cadences from LSST. And then lastly, we split those into our 5 different signal models, just by combining some of those different signals and seeing what will be more realistic so that we can kind of capture everything with what we're looking at. So here are just examples of some of the light curves we have, again, using the periodic signal with the quasar noise and the LSST photometric errors and observing cadence. So in the bluish green, I have the just pure signal with no noise, and then the purple is the actual data points that we'd be simulating. And then here is a multi-band one where you can see all 6 bands and how the signal is kind of carried out through them. You can still see the periodic variation there. So some of the first things we've seen with our simulations is first that the smaller mass simulations tend to reject a lot more parameters since they're going to be a lot dimmer. So you can see over here, these two on the left are for a 10 to the 5 to 10 to the 6 solar mass range, and then on the right we have 10 to the 9 to 10 to the 10 solar masses. So there's a whole lot more rejected parameters for those smaller mass cases because, again, they're just too dim to meet our criteria of being able to be observed in at least one band. So we get about 10 times more rejected parameters than accepted for those ones, which kind of results in a longer runtime for those simulations while the code has to loop through and find the correct parameters that will be visible. And as a result of that, we no longer have a uniform distribution in the accepted parameters for the low mass cases. So they're kind of skewed towards higher masses within the range and lower redshifts. Because again, those will give us slightly brighter light curves. So in summary, we have these simulations for a broad range of physical binary parameters, as well as signal models, so that we have both sinusoidal and non-sinusoidal signals in there. And we have realistic quasar noise, as well as the LSST photometry and observing cadences applied there. And we've already started identifying some bias in some of those low mass cases. So from here, we plan to start incorporating some of those higher order karma models in order to see kind of what different noise models will give us more accurate results. And then we plan to use these simulations to train algorithms to search through LSST data and hopefully identify periodic binary signals, with those noise-only simulations being our null case that we can test false positive rates and see if it's accidentally identifying just a quasar noise as an actual signal. And once we finish all that, we'll be making the simulation data sets and the code publicly available. Thank you for listening, and thank you to all of the people who helped me work on this and get here. And for the AGN Science Collaboration Variability subgroup, we've all been working kind of on this together, and they've been helping me with anything that I wasn't sure on. But yeah, I'm welcome to answer any questions.
Yeah.
I have 2 questions. I'll try to go very quickly. So first, Meg Davis at the University of Connecticut has been doing broadly similar work, but I'm sure there's differences. How does your work compare with her? Do you get similar results? Do you have different techniques?
I'm not sure specifically what she's doing, but I know we have talked a bit on that because she's at some of the variability subgroup meetings. But I'm not sure exactly what method she's using.
She does have a published paper on the topic, which might be useful.
Yeah, for sure. I should check that out.
The second question, you kind of mentioned at the end that this issue of assessment of false positives, which clearly I think is a challenge. So if you look at the currently reported periodicity candidates, I think maybe 200 or something now, do you have an assessment based upon your work as to how many of those are likely to be false positives? Is it 80% or 90% or 100% or?
Yeah, I don't know the exact statistic, but I know it is estimated that there are a lot of false positives in there, especially as we're learning more about higher orders of, damped harmonic oscillator, higher than that. Different models are working out better. So I don't know the exact statistic, but I know it's a good portion of them.
Yeah, that'd be a very useful thing to check into. Yeah, okay,
There's over 1,000 now, and it's probably at least 90% of them false.
Yeah,
Okay.
okay.
No questions?
That's one of the actually that's years.
Lisa, do you want to unmute yourself if you can?
Yeah, it's not a question, but thanks, Edin, for presenting this work. It's about the comments on the Mac Davis's work. That's also have a similar motivation. But I would like to point out that the Edin's work is more based on the physical models, based on the simulated dynamics of the two binary, the black holes and the accretion modulations and some self-lensing, and of course Doppler boosting. But the Mac Davis's will also have the similar features, but the periodic signal and the Doppler boosting. But I would like to say that the Edin's works more based on the physical, the configurations and the dynamics of the two supermassive black hole. Correct me if I'm wrong, Edin.
No, yeah, that's right.
Thanks.
A very good question from Chris.
So in the light curves you showed, I could always pick out by eye the binary signal, and it was dominating the total variability, and it didn't look like there was much room for the AGN stochastic variability. Do you match the amplitude of AGN variability to the amplitudes we normally see?
Yes, yeah. So we use some kind of correlations that were already determined in some other sources to get those, and then use things like the total mass that we had selected for the system and the average magnitude in order to determine the amplitude and the time scale there.
Because 0.2 of a magnitude is what you would typically see in stochastic AGN variability, and yet that's more or less the total of your light curve up at the top.
Yeah, that is kind of part of the struggle with trying to determine whether we're seeing just AGN variability or a binary system, is that they could kind of be similar in amplitude there.
Yeah, okay.
Okay, thank you, Edin. And Carroll. Move on to our next speaker with Carroll. That's what we're speaking.
Who knows that's scary, honestly.
Transport has to be basically. It is transit. Not sure.
Okay. What? Okay, cool. I'm Chris Carroll. I'm a LSST Discovery Alliance Catalyst Fellow. I'm working at Washington State University. My primary supervisor is Vivian Baltasari. And I'm also working closely with Roberto Assef and Gordon Richards on my attempts to simulate the type 1 quasar luminosity function for LSST. So I talked a little bit about this briefly at last year's summer meeting, but I was just kind of biting into it. Made a lot of work under the hood, so to speak, in the meantime. So I just want to kind of put this back on your radar. So the main motivation is that given any prescription of how you were to build a universe, you could predict the AGN luminosity function. And the method that we're going to do is a completely catalog based, is essentially building spectral energy distributions for combinations of galaxies and AGNs, and trying to do this in a very top level, fast, modular way, such that if anyone else comes along with a different prescription or wants to use some different spectral energy distribution models, they can just kind of plot these things in and it will run. It's a very lofty goal. It's a lot harder, I'm finding out. But anyway. Yeah, so this is kind of a status report, just kind of like as I'm working my way towards trying to wrap up some details and move forward. So bear with me because my question to the collaboration is, why practice your talk if 1 hour before you're going to rip to pieces and make new slides? So please bear with me here. And then Matthew came and said, you know, they were talking about luminosity functions. They were looking for you. And I said, oh gosh, here we go. Okay. So building a universe. This, I just realized after building this slide 1 hour ago, that you should have put this on the bingo, because how many times can you tell people that you are building a universe and they don't look at you funny? Okay, I have three circumstances where that could happen. Talk to me after, and if you can name one that I'm not thinking of, I'll give you a present. Okay, so we're going to use Roberto Asif's low resolution templates. There's one for each of these stellar populations and an AGN template. The idea is that you can just kind of put these in, it will crank through, it will create your object, and then at the end you can kind of collect your sample, move on. Okay. Again, like I was saying, the idea is that you should be able to come up with a different, if you want to use different templates, you should be able to just plop them in. It's kind of cool. Like, the idea that I had in mind was also like, what if tomorrow they decide they're going to build a different telescope for a different wavelength range, that this would still work? Like, suddenly you just put in IR templates and now you can do this in the IR. This was my goal. We'll see if it's working. Okay. So the first thing, we're going to populate AGMs. We're going to start with the Shen 2020 quasar bolometric quasar luminosity function. The idea is that you can essentially just draw pairs of luminosity and redshift that you can then create these objects around. All the details of how I do that. Okay. We can talk. Populating galaxies. This is the hard part. So galaxies can have complex star formation histories. There was actually a paper at the beginning of this year, Witten 2025. This is like a redshift almost 8 object or something, and they're finding that it's got its clear Balmer break, but then it also has emission lines, and they find like, oh, this is going through a rejuvenation process. And so if you want to build an observed luminosity function off of something, but you want to be able to find outliers or then you can't necessarily build it where you will bias yourself. Okay. And this is where I'm getting hung up the most, right? Like earlier, if you were in the catalog or the first AGN catalog session, right? Gordon said, well, why don't we change, how we do this for the different eddy fractions or something? And the idea is that, if you create objects you wouldn't expect to see, then you can either prove they don't exist or find out how you observe them. And so this is kind of the point of this, is like, can we build this really general thing where, this sample you're creating has all these weird objects that you could potentially find, but at the same time, you can't just build a simulation and say, well, this is probably how it works. You have to test it on things that you know. And so if you're building things that might not exist, and then you're trying to test it on things, this is where it gets a little tricky. So building the galaxies, the total SED, the stellar population of the galaxy, is like my biggest challenge. Okay. I should have changed to that before I said all that. Okay, anyway. So at this point, I have done a lot of work over the last year since the last meeting on how we build this galaxy. I would love to talk to you about it, because if you have a better idea. Anyway, we're going to match these to the SDSS DR3 quasar luminosity function from 2006. Yay, we're starting to get LSST data, so let me show you SDSS. Cool. All right. If you were to just build bright type 1 quasars with minimal, they're completely swamping out the galaxy, I'm finding in some large sample, that we're kind of matching what you would expect for the same color range, right, that we get out of the DR3 quasar paper. If you then turn on adding galaxies, you might get something we saw earlier in one of the talks. Someone was saying, well, look at this area here in color space. This is probably things we don't. This is the whole point of what I'm having issues with. But we can see, well, no, you can't see because well, anyway, the locus is still around here and things are spreading out. So we're like kind of in the right range, right? But we got all these objects that have a red color and I minus Z, and this is, kind of where I'm making some tweaks. Anyway, we're on the right track, I think. If then I also let this run and create a huge sample and then use similar selection criteria that would have objects fall into the 2006, into this luminosity function that Gordon built, I'm getting similar objects, similar redshifts, similar absolute magnitudes, right? And so this tells me, okay, we're like on the right track. Like I said, I just built this slide. There was one more point. I put it on the presenter notes, but I don't remember. Anyway, moving on. Talk to me later if you need any questions. All right. So then, okay, what if you build the luminosity functions, right, in the same redshift bins? Don't mind this turnover. I know what's happening. But from those humps on, we're getting similar results, I think. Similar enough to know, okay, like these things that we're building we're on the right track. Yeah. This is big for me. Okay. I've been dealing with building these galaxies for a while. I'm getting a little upset at it, but this was a good result. Had to put this in here, thankfully. I already showed that. So what happens when you build it an hour before? Okay. So real next steps. Okay, there will be a draft before the end of the year. I guarantee this. Okay. Even if it's like 2 days before the end of the year, I'm sending it around. Okay. But what will end up in that draft will really depend on how far I get down. Okay. Definitely need to finalize how you build a galaxy before you can send around that paper. Implementing AGN reddening, right? We saw Demetra, you gave the talk about obscured AGN and variability. If you know my work, I love obscured AGN. So also we're using the bolometric luminosity function, which means there's a bunch of obscured AGN in there. And can we tease them out? We have to use a proper reddening model. These things go very high redshift. Which one do you choose? That's really the implementation aspect is already built in. I just have to choose the right model. But you can't choose the right models. You know what you're doing. I have to build the galaxies. It's a process. Okay, applying AGN variability so that you can kind of tease out light curves. Line out forest for really high redshift objects, right? Okay. And then switch on LSST, right? I'm doing this for SDSS, but it's all built and LSST is there, right? And I just have to flip the switch. And then, ta-da, the draft, I don't know, December 30th, who knows? Okay, that's it. Thanks.
Any questions?
Why do we apply AGN variability in this case? Well,
I get that. Okay. Right. So this should maybe be here and not in the tab, right? It should be like, oh, maybe we'll get to this and you might be able to do something with it. There was an initial, I thought, that we could do, hit it with OpSim, right? And then actually get out from these get out light curves, that would have AGN variability built in, but then also, right, understanding something about the cadence of the observations.
Okay, so yeah, you wanted to explore that it wasn't for the
should be here. Should be moved back and should be under that tab, right?
I thought it was needed for.
No, sorry, apologies.
So we've played this sort of same game from X-ray point of view of build your own universe. We did it by piggybacking off the illustrious T and G simulations, and then using the conditional probability distribution of an X-ray luminosity given a galaxy stellar mass and its redshift. And you could imagine both things would interact. Have you tried to compare with those types of results? I believe that's what the agile people do as well. Do you get consistent results with them or with the Zhao et al. Paper where that does its own build your own universe type thing?
I have not compared
Okay.
yet.
There's this challenge of going between X-ray and optical.
Right.
Yeah.
Right, I have not compared yet, because, and this, in my mind, the idea was, I don't wanna bias myself by using a particular method or, right, but then, now that I have results that I'm starting to trust, I should go and compare, you're right.
Just interesting.
I haven't yet, though,
Okay.
no.
You can take the galaxy stellar mass function, the conditional probability distribution, and thereby generate the X-ray luminosity function.
Mhm.
So we know it works that way, but we've never tried to work it back to
Yeah.
the optical luminosity function. So it'd be interesting to connect these things up.
Yeah, I can just comment that I think we are compatible within the bolometric correction of Shen.
Okay,
Yes, basically we are reproducing the X-ray luminosity function, the quasar luminosity function, and then Shen is putting it all together and deriving the bolometric correction. So
basically,
within this.
it ties up correctly, it links up where everything's
Yes,
going. Okay,
yes.
good.
Any more questions? No one online,
No one online.
right? Okay,
So outside, let's just switch this up.
oh, okay.
Sorry, just one more question.
Yeah.
So could you elaborate on the motivations of the Lyman alpha forest, the implementation in your simulation, particularly, I mean, you simulating the luminosity function bivariate in terms of luminosity and the redshift space. Then if that the Lyman alpha forest is really just, which aspect do you think it's more relevant in terms of your science in simulating the luminosity function? I mean,
That
I just try
depends.
to understand, yeah, is it why is it important or how important it is?
It really depends on where we decide to cut off the redshift of the sample, right? The idea was if we could push this to really high redshift, then the Lyman alpha forest could play a part, right? But that is like really way down on the list. That's I would be surprised if I observe enough sources that it would matter as much. I think, does that answer your question?
Yeah, I mean, partly I understand the motivation, and then more or less, if it is so important, then you have to think the proper way of prescriptions to implement it, right?
Right. Yeah. Yes.
Okay. I'm looking forward to your the result later. Thank you.
You too. Thank you.
Okay, so thanks again, Drew. Okay, but it seemed like a really timely transition there. Because I'm gonna talk all about the Lyman alpha forest, even though this is a quasar meeting. Actually, it's only a little bit about the Lyman alpha forest. So let me just share my screen. And then, oh my gosh, oh, it's so big. Sorry, there's just like all of the Zoom. Oh, and it didn't. Oh, okay, sorry. Okay.
Right, just
Yeah, just put it on top.
start showing again with just the presentation. Yeah.
Okay. 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 All good. Okay. Perfect. All right. Hi, everyone. My name is Catherine Kama. I am a third-year PhD student at the University of Cambridge. I work with Richard McMahon and Paul Hewitt and Matthew Temple. I'm going to talk today about photometric redshift selection and characterization of high redshift quasars. So to start things off, for me, I would define a high redshift quasar as above redshift 4. But I know that high redshift means different things for everyone. But just for this talk, it's redshift 4 and above. And specifically for the quasars that I'm talking about, these are type 1 quasars where the SED is like entirely dominated by the AGN, or mostly.
So high redshift quasars are really interesting. They allow us to constrain the growth and formation of supermassive black holes in the early universe. We get to learn about the coevolution between supermassive black holes and their galaxies, and they also allow us to probe the changing state of neutral and ionized gas in the intergalactic medium. The thing about them, though, is that they are very rare, and this is, you know, a twofold problem. One, because there aren't that many of them, because it takes a long time to grow a black hole that big. And two, because they're so far away, they're faint. We're just like in the last 20 or so years, kind of getting up to the kinds of instruments that can detect them. So there's roughly 1 million quasars. And of those million, we have above redshift 4, 4,300, above redshift 5, 1,000, and then it drops off 300 above redshift 6, and 9 above redshift 7. And just a disclaimer, these are the same numbers I used last year at this meeting, so they are probably wrong now, especially with DESI. But yeah, and so this is just showing, you know, the evolution of the ionization state and galaxies through cosmic time. So if you want to find a high redshift quasar, the traditional way you would do it would be using, you know, things like morphology. Is it a point spread function, or is it, you know, extended? And then the color dropout method, or or color selection. So this is just an example of a redshift 5.7 quasar. And so essentially these techniques leverage the fact that because of Lyman alpha absorption along the line of sight with the quasar, the objects get much redder, and you essentially get like almost a step function as you go up to higher redshifts, and the SED moves through the different bands. So this is a really, really good way for finding high redshift quasars. Most high redshift quasars have been found in this way or something similar, but it is also really, really good at finding things that are not quasars, like cool dwarf stars or compact red galaxies. In fact, when you're doing this kind of color selection, you end up with pretty high contamination rates. So like 70% is not unusual. And this is because, you know, a cool dwarf star is a dim red dot, which is also what a high redshift quasar is. But also there are a lot more. Dwarfs are, you know, the most luminous kind of star. So you just see a lot of them. And because of this contamination effect, if you want to study your high redshift quasar, you need to get a spectra of it. One, to make sure it is a quasar, and two, to, you know, get the redshift, and then you can work from there to learn more about it. However, getting spectra for everything that you think might be a high redshift quasar is not sustainable for the amount of data that we'll get in LSST, which I'm sure everyone knows here. There's not enough spectroscopic observing time in the world. So, as I said before, we've got about 300 quasars that we know above redshift 6. We expect, with just the first year of LSST, that the number of detected quasars will go up to about 3,000. So that is a 10 times increase. But that's just the detected quasars, not to mention all of the contaminant sources that we will also detect as well. So we've got so much data and just so little spectroscopic observing time. So the solution that we are proposing for this and that we're working on is SED fitting to both select high redshift quasars and discard contaminant sources, but also study and characterize the quasar candidates themselves. And so these are things like the photometric redshift of the object, intrinsic properties like their luminosities, reddening, also looking at just high redshift quasar populations as a whole, you know, speaking of luminosity functions, and just finding the really interesting objects that we want to spend that precious spectroscopic observing time on. So just the gist of SED fitting and our method here is that if we have an object that we want to look at, say it passes some very basic color selection cuts, we will then fit this fit this object with quasar, galaxy, and dwarf model SEDs, and try to optimize all of them and see essentially like which one fits the best, comparing goodness of fit metrics to determine, you know, is this a likely quasar candidate? And if it is, what are its properties? So, you know, when you're creating these model SEDs, you've got three main components. You have your intrinsic rest frame object SED. So this is going to be like your quasar, its luminosity, its intrinsic reddening, and then you have the redshift depth that it's at. And so you have your, you know, actually redshifting spectrum, but this also includes the contribution from neutral hydrogen absorption along the line of sight. And this is very important above redshifts of 2. Below that, not so much of an issue, but above that, it has a significant impact on the spectrum. And then finally, you have your instrument and your atmosphere. So that's just taking your model spectrum and, you know, putting it through the band passes. So the first part of this is the quasar model. So for us, we use the Temple 2021 parametric quasar model, and we specifically look at the redshift, the intrinsic reddening, and then the luminosity, host galaxy contribution, and emission line strength all rolled into one parameter, which is the MI at redshift 2. And you can do and like look at more of these things, like do more parameters and stuff, but just because we tend to work with maybe 5 to 12 bands, like keeping the number of parameters down is, you know, our objective. And then something to note is that these are continuous parameters. These are not like a grid. So this is just an example of like how changing the different parameters will change the shape and the photometry of the SED. So the quasar model was very fancy. The models that we're using for the galaxies and the dwarfs are a lot more simple. They're just like template-based models that we interpolate between. So the second part is intergalactic hydrogen absorption. And so this is actually what a lot of my work on recently has been. I'm sure you've all heard of the Lyman alpha forest before. It's the absorption that you get above about redshift 1, onwards all the way to about redshift 6 when just all of the flux drops out in a Gunn-Peterson trough. And it happens because of cosmologically distributed neutral hydrogen clouds along the line of sight between us and the quasar. And so the kind of features that you see in IGM absorption are your Lyman alpha forest and the lower or higher order transitions, so Lyman beta forest, delta gamma, it keeps going. Your Lyman limit systems, which will occur, you know, bluebird of like the rest 912 Lyman limit, and then damped Lyman absorbers. And then while in an individual quasar, all of these lines are they are individual clouds of gas. You can take the average over many lines of sight, and the absorption actually acts as a very well-behaved function of redshift, increasing with higher redshift. And so this has a major impact on the observed SEDs of these objects. And if you're measuring a photometric redshift, this is one of the driving factors for what you're measuring above redshift 2. So it's really important to get this correctly. There are existing models that are used in tons of SED fitting codes, like the Madao model, the Makeson model, and the Univ model. So I am here with a new model. So this is the key updates for this are basically I have taken newer data, new observed things to sorry. I've taken newer observations of things, observables like the optical depth of Lyman alpha as a function of redshift, and the distribution of Lyman limit systems as a function of redshift, and applied it to the underlying mathematical equations to describe, the stochastic distribution of these objects. So the key thing here is I've included new data for above redshift 5. So at the top is my model is in black, the data points are in gray, and then the Matheus model is in pink, the Mixon model is in orange, and the NOIRLab model is in green. So the key difference is that at redshifts above 5, my model, fits the data a bit better than the others. And then this here is the transmission function. So for redshift 2, 3, 4, 5, and 6. And the key things to see here are that the Matheus model in pink has a lot more absorption in the Lyman series as compared to the newer models, which all pretty much agree with each other. There are a few small differences between mine and the other two models, namely at the Lyman limit systems at low redshift and the Lyman alpha absorption at high redshift. So I'm using that model in my SED fitting, and let's see how it does when we're finding the photometric redshifts of quasars. So I was testing my SED fitting code on a sample of 13,000 quasars from the Million Quasars catalog, and specifically only the quasars from this catalog because there are not quasars in that catalog as well. And I'm looking at objects with spectroscopic redshifts between 2 and 7, and using the U, GRIZ, YJHK, and WISE1 and WISE2 bands. However, it is not homogeneous. This is a mishmash of data. So some things have 5 bands and some have 12. And again, we're looking at the redshift, the MI, and the reddening, and the log luminosity. So these are the results that we get. It is a pretty good fit, I would say. We've got an average, we have a median bias of 0.001 in redshift, between redshifts 3.5 and 7, and a sigma mad of 0.16 in units of redshift, and then an outlier rate of 0.2%. So this is great, but I just kind of want to show the impact that your IGM model choice can have on your photometric redshifts. So if we use the Matheus model and keep everything else the same, these are the results that we get. And in the same redshift range, we see a median offset of 0.14. So this is underestimating the redshift, and this is because of too much absorption. It has a slightly better sigma mad, so slightly less spread, and a slightly smaller outlier fraction. Additionally, it seems to perform better between redshifts 2 and 3.5, but this might be a selection effect or just something that we need to fix with the model. Finally, the actual selection part of this is still a work in progress. We are using the DESI Z greater than 5 quasar candidates, which all were released in DESI DR1 and have, the spectroscopic follow-up for them, and trying to, learn how we can improve things, especially the contaminant models, to try to find our quasars. Very quickly, the future, we'd like to find some quasars with LSST in one of the fields released in DP1. There actually already is a known quasar there at redshift 5.3, which is very exciting because given the small area of the field, we don't really expect to see very many. And finally, conclusions, SED fitting is a really valuable tool for studying high redshift quasars in the era of LSST, and we can measure accurate and unbiased photometric redshifts, and the IGM model, absorption model significantly affects that. For future work, we're going to be testing our selection, applying it to LSST, DP1, and making some predictions for the future. Also, we're hoping to submit the IGM paper by the end of this month. So please keep an eye out for it. Be on the lookout. And if you're interested in using it, like, please get in touch. So yeah, thank you.
Thanks, Justin. It was really nice work. I'm wondering, so for the LSST data, so how well this model can perform when you don't have infrared observations,
Yeah.
but just with LSST lens?
Yeah, so I think I showed a picture, or sorry, I showed a plot of this last year. But you're still able to get like pretty accurate and good photometric redshifts. That's because the most of the redshift information is in your like optical and infrared bands. So your UGRIZY. But it becomes an issue when you're looking at the selection and trying to figure out, is this a quasar or is this, you know, a cool dwarf for a galaxy? Because a lot of that information is in the infrared bands. So you need to maybe rely on other selection methods for that.
Questions? Plenty of questions. Who wants to go first? You? Okay.
So you mentioned that, you know, your IGM model does have some stochastic elements to it.
Mhm.
Have you tried to do a Monte Carlo simulation to work out, you know, for a given line of sight, the range of corrections one might expect, as opposed to just the average value, or is your focus entirely on the average value?
Yeah, so we're focusing on the average value here because like with our work, we're looking to fit as many as we can as good as possible. So the average is like what works for us. However, we have been thinking, especially at the low redshift end, the Lyman limit system part of this model is so okay. In the Lyman series, this is actually the average is okay because you have so many lines, like if you're looking at an individual spectrum. But when you get to the Lyman limit system part of it, in a single spectrum, that's going to look more like a step function than this like smooth curve. This smooth curve is like the average of like, you know, how far away this Lyman limit system is from the source object, like at a given quasar. So you could actually fit for the position of the Lyman limit system as like a free parameter when you're doing these kind of SED fitting. So like that could be one way to, you know, better model that, but I haven't done anything more yet.
Could be a useful thing, yeah.
Yeah,
Great talk. So I wonder how helpful it is to, after applying your engine model, can you discriminate those round of contaminants or like low redshift gases?
So that's kind of the part that I'm working on right now, is the discrimination part of it. I haven't looked at specifically how the choice of model affects that. I have, it doesn't particularly affect like goodness of fit metrics or, you know, like your chi-square, whether you use the Medal model or the Inouye model. Those are very similar to each other. So if you're using those to, you know, like choose, you know, is this a quasar? Is this a brown dwarf? It won't have that much of an effect. But yeah, I'm sorry, I don't have a better answer for you yet, but maybe in a couple months.
We also have questions online. Sorry, I don't know who raised their hand first. William, maybe. William, with yourself?
Yes, thanks. Very interesting talk. Thank you. I was wondering, besides the estimating of the redshifts themselves, do you have an estimate for the runtime? Because I imagine that you'll be wanting to run this on all of the sources prior to knowing what kind of objects you're looking at.
Yeah, so it takes about a little over a second if you want to run the quasar and well, actually, I think it's like about a second if you want to run for one quasar. And it is like parallelizable. So, but you know, I am not working with a ton of compute. I'm just working this on my like desktop in my office. So normally what I would do, and I think what this was made with the goal of doing is applying very lax color cuts, so we're not fitting everything under the sun, and then going like from there. So in the tens of thousands of objects is like doable within an hour, but trying, yeah.
Okay, cheers. Thank you.
Okay, Bindu, can you unmute yourself?
Hey, Katrina, can you hear me okay?
Yeah.
Great talk. Thank you. So I think it would be useful if since you are gonna make the code available, but also it would be useful for you to get involved, like when the data comes in, to use the code and to filter out the high redshift sources, and the multi-wavelength follow-up groups can follow up those sources. So I think we can work together along those lines to get things done together. What do you think about that?
Yeah, that sounds like a good idea. I'm really happy. I would love people to use this, and I hope it helps. So yeah.
I'll drop you an email to discuss this further. Thank you.
Yeah, thank you.
Okay, so I think we should stop here. And if you have any further questions, you could post them. You can post them in the Slack channel. Let's thank Catherine and all the speakers of the session again. Want to copy and reconvene at 10:04. Something I guess you lost my brain.
Yeah, so maybe the changing look or variability amplitude, you can play around with all sorts of slides.
Okay.
No, it's 40 degrees. The code Good. So you want to get
No, it's not very good. I think I'm trying to grab it. No. It's going up pounds. Yeah, it's a come off full. I'm good.
Yes, do I sign into the Zoom?
Yes.
Cool. Find it, sorry, I'm having everybody up.
Oh, shifted by the let's see, that's maybe. Really, okay.
You don't really care what you.
Yes, I think I'm there.
Okay.
I should keep it muted, right?
Yes, please.
And everything off. I'll leave my camera on so people can get this weird angle of me. Let's see. Perfect. Okay.
So you're good. 2-minute warning when you get there. 13 minutes or so.
Okay, sounds fair.
Okay, we'll start with Amy Secunda talking about long negative legs.
Great. Hold on. I am gonna just pause quickly so I can minimize this so you can see more of my slides and less of me. Okay. Awesome. All right. So yes, for those who don't know me, my name is Amy Secunda. I've been now in this Rubin Agent science collaboration for I think 4 years. So it's always like a highlight to come to these summer meetings. And yeah, so I'm going to talk today about some of the work that I do looking for what I like to call the long negative lag. And don't worry, I'll go into more detail about what that is. which I just think Rubin is going to be the ideal instrument for. And so I've been doing some prep work to kind of develop machine learning models to help us find these long negative lags efficiently. Okay, so most of us are probably familiar with the Shakura-Sunyaev standard thin disk model, right? Which says you have a geometrically thin but optically thick disk. But what is still kind of being debated, but what I argue is that, this model has been around 50 years, but it wasn't really designed for AGN in the first place. And it's not really correct for AGN. So for example, there's both observational and theoretical evidence that there is variability in light curves from AGN that are just on timescales shorter than the thermal timescale predicted by the standard thin disk model. And I'll just do a very brief plug for two of my papers where I actually simulate AGN disks using multi-wavelength radiation magnetohydrodynamic simulations, where I self-consistently evolve the turbulence in the disk and then look at how it impacts light curves emitted from the disk. So this is one of the light curves emitted from one of my simulations. And I think we would all agree that it varies on a range of timescales. But what might surprise some people is there is no X-ray variability in this simulation. This simulation is just the variability emitted from a chunk of an AGN disk due to its intrinsic variability, due to the turbulence caused by the magnetorotational instability and convection in this particular case. So anyway, that's my brief plug, but none of this really makes any sense in your standard thin disk model, which says you should have a pretty laminar disk. Other departures from the standard thin disk model is that there's been some observational evidence, both from reverberation mapping and from micro lensing, that the radial extent of AGN disks is larger than predicted. And then finally, there's both theoretical and observational evidence of these flaring accretion disks. So instead of having a constant thin disk as you move outwards in radius, there may be regions of the disk where the height of your disk increases with radius, giving you this kind of flaring structure. And I'm actually going to talk about how this is related to the long negative lag, and essentially how the long negative lag is a fundamental test of the standard thin disk model. So, okay, at long last, what is the long negative lag? So, as I said, we see these fluctuations that happen in AGN disks, and we see that they impact the light curves emitted from the regions where they happen. So let's say you have a fluctuation in your AGN disk in an outer cooler region of the disk that then emits in the optical. Well, then you would see it impact the variability of this light curve. Then, over an inflow timescale, you can have that little fluctuation get accreted inwards to an inner hotter region of the disk, where then it can impact the variability in a bluer waveband that is emitted from this hotter region. And so we call it a long lag because it happens on the inflow timescale as opposed to the light crossing timescale for a discontinuum lag. So that's going to be a much longer timescale. And we call it a negative lag because, your continuum lags, they come from the inside out, and this goes from the out in. And so the question is, how much longer is this inflow timescale compared to the light crossing timescale? So according to the standard thin disk model, this inflow timescale is on the order of 100 years, which, we would not be able to observe because we haven't even been looking at AGN, not really for hundreds of years. However, you can see that this inflow timescale, most importantly, depends on what we call the aspect ratio of the disk, or the height of the disk over the radius, right, to the -2 power. And so if we relax the assumption of having an ultra thin disk, and we say this aspect ratio, instead of being 0.01, is 0.1, because it's to the -2 power, that's a factor of about 100. And so instead of talking about hundreds of years, suddenly we're talking about hundreds of days, which maybe we can measure in long baseline light curves. And so we actually think we detected one of these long negative lags for the AGN Farrell 9, which I know Scott will talk about that in detail in his talk. Not this, but his work, and also why, Farrell 9 is a bit of an oddball. So, take these results with a grain of salt. But we were able to detect a long negative lag going from our reference waveband, the W2 band in the UV, all the way out to the optical. And this long lag goes from about minus 30 days in the UV to about minus 70 days in the optical. And so we can use the dependence of the inflow timescale on the scale height to use this to create a model for the height of the disk as a function of radius. And so what we show our best fit model in green here, and what we find is that the height of the disk goes as the radius to the 3.6 power. So that is some really dramatic disk flaring. So again, this is an early result, take it with a grain of salt, but it kind of shows that it's interesting to look at this and it's possible to derive information from this. So a lot of the work I've been doing is trying to do some forecasting for can we do this with Rubin, in particular in the deep drilling fields where you have very reasonably high cadence and you'll have ultimately a 10-year baseline. Also interesting is that you'll have kind of the 6 different wave bands. So that's very useful if we want to do kind of what we did for Feral 9 and look at the lag as a function of wavelength. And so to do this, I make Mach-like curves, not the really nice, expensive, hard to make Mach-like curves like I showed for my simulations, but the cheap and fast light curves that I can make to train a machine learning model on. So I make damp random walk light curves. I use Wei Zhang's easy tau to generate that. It's really fast and nice. I add deep drilling field LSST cadences and errors. And then I put in a short lag, which is what I call your discontinuum lag of 0 to 10 days. And then I put in a long negative lag of either 0 days, so no long negative lag, which, are null case, or of anywhere from minus 10 to minus 500 days. And then finally, this is kind of important, is that we really expect your discontinuum lags to be a much stronger signal, right? If the long lag were a stronger signal, we'd have already detected them more often, even with current baseline data. And so we really expect the short lag signal to be much stronger, to the X-rays to be the main driver of variability. And so we have to set the amplitude ratio of the long lag versus the short lag that we're using to reprocess these light curves. So all that is to say, the long lag is at most even with the short lag, and then we go all the way down to 10 to the minus 3, which would make it hard. So here are just a couple example Mach light curves where you can see we reprocess with a long lag, and you can see we sample in the bottom panel, right, with the deep drilling field Rubin cadence. And so as a test, we run an interpolated cross correlation method on these and javelin on these, right? So the line through the middle is the 1-to-1 line of the true lag. So the lag we put into our, into our Mach light curves. And on the y-axis is the light curves the long lag predicted by these methods. So you can see for the interpolated cross correlation, it is reasonably accurate. When the amplitude ratio is high, right? When the long and short lag are nearly even strengths. But as soon as you get to that long lag having a weak amplitude, which again is kind of what we expect, these are optimistic, these are realistic. It really can't measure any long negative lag. So, you have about 2/3 are accurate within 20 days, but then you don't get anything, right? So unable to recover lower amplitude ratios. Javelin, you have this aliasing problem, which I think is well known, where, if Javelin is unsure, it'll just say, well, there's a really nice seasonal gap of about 200 days. What if that's the lag? And so you can see, right, like there's just this overabundance of 200-day lags, which means when we try and use Javelin to do this, we just can't believe any lag it returns between 150 and 250 days, because it's just the seasonal gap. It could be real, could not be. So we again have about 2/3 that are accurate within 20 days. But in summary, they can be very accurate or they can be completely useless. And this happens again when the amplitude of the long lag gets weaker relative to the short lag. And so the question is, can machine learning do better? Hopefully, yes. Otherwise, I've wasted my time. So here is a first example of what we can do. So I use a transformer model, which is very useful because it is able to It's very useful for time series data. And so here's an example of for those same Mach light curves, how the long lag transformer does. I should say I have showed this, there are more light curves plotted here. So this density in here is actually very high. And so overall, we get that 88% are within 20 days of our input long lag, and 70% are within 10 days of the true lag. So that's actually pretty good. You know, we've increased our ability, and it is not quite as biased against these weaker long lag amplitudes. However, I mean, I'm sure you're all noticing, right? For you know a decent fraction of cases, we put in no long lag, and it gives us any answer that falls within our parameter range. And that's really bad because, again, we're just not even sure these long lags exist. So if we, you know, we're not sure they exist. So if we want to believe our results, we really need our model to exclude anything that has no long negative lag. And so we fix this by we pre-process it. So we take our Mach light curves and we run it through another transformer model, but this one is a binary classifier. So essentially, it either says it has a long lag or it doesn't have a long lag, right? So we give it 50% with no long lags, 50% with long lags. We ask it, does this have a long lag or not? And in the end, we actually have gotten it down so that it's only 0.05% contamination. So I think that's pretty acceptable, right? You know, you give it 100, you know, Rubin light curves, and if it doesn't have a long lag, it will almost, you know, almost zero will be detected. So that's pretty good. And it keeps us at 91% completion. So, you know, 9% that do have long lags are not detected, are weeded out in this stage, but that again is very acceptable. And so I'll just quickly say between the last plot I showed and this, there were a couple other upgrades. We moved to a bigger transformer model, and then we also increased the range of the long negative lag that's possible up to half the length of a Rubin light curve. And so this is our latest result, which is now 93% accurate to within 20% of the true lag. But you can see we no longer have this zero problem. I mean, again, this is the 0.05% contamination right there. Those three, you know, out of all that are plotted here. And it does really well, and it does really well across amplitude ratios, right, all the way down to these really low amplitude long lags. And it does really well up to really long lags relative to the length of the light curve. You know, again, you can see it start to do less well as it gets to the longest, but it does really well. And, you know, I'm still looking through, but it looks like, you know, again, Javelin really can't handle lags these long. And the ICCF also, you know, again, returns a lot more zeros. So yeah, so I'm feeling kind of optimistic about using this and would like to start applying it to ZTF light curves while we wait for Rubin data to come in. But I think that this is a really fast, powerful way to go through a bunch of Rubin light curves and look for these long lags. So in summary, right, we think propagating disk fluctuations produce these long negative lags on the inflow timescale, which, because they depend on the height of the disk, can provide a fundamental test for the standard thin disk model. We think we already detected one for Ferrel 9, but we want to detect, you know, hundreds to thousands of more, which is what Rubin can help us do if we have the right tools. And I think this machine learning tool will be really useful for that. So thanks. Excited for questions.
I have various questions, but I'll stick to one
Yeah.
now.
Okay.
So when you're simulating your light curves, are you giving, so for instance, you had one sort of intrinsic disk, which is giving you a long lag, and then your lead processed X-ray light curve. Do they have separate timescales?
Well, so we use a Gaussian response function for both. And so, right, so the timescale will peak, right, at around the mean of the Gaussian response function.
Okay, but this is when you're generating the light curve, right?
Yes.
So, but is the mean of that Gaussian response function the same for your one that's, let's say, is influenced with this than the one that's?
No. So yeah, so right, so the mean is the long or the short lag. So one is like, you know, a few days and the other is like 100 to hundreds of days. So the mean are different and the standard deviations of the Gaussians the widths are different as well.
Okay.
So yeah.
So a lot of these models are based on the idea that we've got stochastic fluctuations on a stationary system. But as I was showing in my talk, there are systematic changes in the SED that mean that if you do too much variability, you're no longer you're changing the source geometry. So how do we distinguish between changing the source geometry and response signals from illumination or propagation?
Yes, so I guess, right, that is tricky, but I would argue the two are related. So like, for example, some of the fluctuations we see in our simulations are due to convection, right? Which is in some ways changing the shape of, right, the geometry. And right, obviously that will impact the light curve. So I guess at this point, we're kind of agnostic to which of those changes we're seeing. But the question is, do those changes propagate?
Yeah.
If they don't propagate, then we're not gonna see it as a lag. So I guess we're interested in any propagating change.
Yes.
But you know, kind of the finer details at this point, I don't think, you know, I think if we had a lot of examples, we could say these 10 look different than those 10, but right now we don't.
I think the best way to see what actually propagates all the way down is to follow it into the X-rays. We really need some X-ray data to go with all of this.
Yeah, I mean, right, at this point, I mean, in some ways, right, we don't necessarily expect these disk fluctuations to one impact, you know, the X-ray. So when we're looking at it, we're kind of cutting it off. Like, you know, even when we did it for Feral 9, we kind of did the opposite of what Scott's doing. We said, we're not interested in the X-ray. We're not looking at that because because at that point you're not in the disk anymore, we think. So yeah, so it's a kind of a different thing, yeah.
You had one fewer talk than you were expected, so I'll let this go on for a little bit, but Claudia, Maria, and then Neil Song online, and then, keep it quick and then we should move on.
Yeah, so I was wondering, this is a very nice talk, how much of this depends on the assumptions you make on the emissivity profile of this?
On the emissivity profile, well, I think to first order, not much at this point because, what's interesting, say for Feral 9, right? Sorry, my network connection failed. Probably because I'm not on edgy room, so I don't have great Wi-Fi, so I can't move backwards. But for Feral 9, like for example, what's interesting is, right, we see that it really flattens out as you go to long wavelengths. So the lag timescale gets kind of shorter between those wavelengths. And so you might say, oh, maybe we have like a vertical temperature gradient and all of that radiation is coming from the same spot, right? Because you have this vertical temperature gradient. But we don't see that in the continuum lag, right? The continuum lag continues to get longer in that region. And so I think by comparing the continuum lag can tell us, is the temperature profile what you expect, right? And is the SED from each region what you expect? And then you can say, but the long lag, how does that interact? Does that make sense? Yeah, so.
Yeah, so I was curious when you introduced the binary classifier and you said 50% lag, 50% no lag, which I guess is the agnostic.
Right.
Is that sensitive? Like your results are sensitive to how much, if you say 40%, 60%, 9 to 10?
Yeah, so that's a good question. As long as you have a sufficient sampling at 0 so that the binary classifier like knows 0 is a valid option, it still works. And we don't set it like strictly at 50%. It's kind of a random, so it's like 49 and 51. But But yes, so as long as there's decent sampling, you know, if we were to do 10% 0 and 90% 1, you know, including a lag, but we had 10 million, that would be sufficient, if that makes sense.
Paolo, why don't you set up while Ilsan asks his question?
Yeah, thanks, Amy. Just quick question. So this approach will find the good candidate with the significant higher disk height. And then is there any alternative way to actually cross-check whether that is true or not? I mean, you have shown the fairly good, you know, performance, but obviously the good to confirm with the other, you know, way of, you know, the observe them. What are the way to confirm it?
Yeah, no, that's a really good question, right? Because we don't want to publish a lag based solely on a machine learning result. So I think right now the use case is you run the machine learning, say with ZTF, since we have those light curves, right? You run the machine learning on 1,000 ZTF light curves. The 10 best looking results, you throw everything you have at it. So you do an ICCF, see if you can find it with that. You know, I didn't talk about Fourier methods, but right, you can also use a Fourier method, which is helpful for finding these long lags because you can try and separate out the continuum and the long lag. So I think that is how you kind of confirm it. You run this really quick method on everything, and then you pay a lot of attention to the best results.
Okay, thank you.
Yeah.
Kofi is going to talk about Desi and Matheus.
Request, yeah, mostly the request update you. And Desi's relevant because finally we have a better way to check how well we're actually doing in terms of AGN samples. And so part of it is, probably most of you heard this by now, but there's a ZTF south that was operating before ZTF a bit, that came from Palomar, then moved south, and it's sort of 10 square degree field of view, big camera. So same basic idea as ZTF. And it's a useful precursor. And the main thing is the time coverage is before ZTF and after like Sloan and CRTS, so it fills in the gaps. That's a useful thing for time series. And I'll show you a better picture in a second. The mouse disappeared. Okay. In the middle, there's pretty good time coverage with sort of 500 visits. So plus, and the maximum number of visits actually, because sometimes there's a dithering pattern in CCDs overlapped in the dither, you can have up to 2,000 visits. So for some things, for bright AGN, it's actually getting LSST-like. And as Matthew likes to say, the actual data volume is and table sizes and stuff are 10% of LSST. So this is not trivial, same for ZTF. And it's just the latest thing showing actual number of visits averaged over 2x2 degree boxes. And these are for bright sources. And what you're supposed to see, if the color doesn't work out here, there are like 800 visits in some stripes. And the average number of visits, say for half the sky, is down here around 150 to 200. So that's pretty good. As you go faint, okay, and this corresponds to a V of about 20.2. If you're looking at RLR going out to 80 kiloparsecs, this does not do forward spectrometry. That's the next thing we're going to do, like ZTF. So as you go fainter and go past the completeness of which this is, you start losing observations basically, but there's still of order 100-ish, okay, over quite a bit of sky, and that's plenty to find AGN. All right. The cool thing about it, good and bad, is it has one color, one filter, okay? Sorry, one filter. That's bad, okay, but it's also good because you don't waste time going back and forth, so you have good time sampling. So the idea here was to get maximal time sampling on the telescope and forget about color. The good thing about the filter shape is basically G plus R. So if you add these two flux, this one. So Sloan always has simultaneous G and R. So particularly when you compare to Sloan, you can match things exactly to percent. So that's very useful. And you can go back in time, and I can show you some earlier, but don't have time to do it. Okay. And then what we did to make things work, this telescope camera is full of all sorts of nonlinearities that are time variable. So we cheat and we go match against standard stars from Sloan, Delve, or Pan stars. Okay. And this just show you for brightish objects, it actually works. So these are a bunch of standard stars, Stetson stars, for example. And then we derive magnitudes from the pipeline and the average observations to get rid of outliers, okay? And then we're just testing for the mean calibration level. And you can see it's dead on is sort of percentage, 2% accuracy. So, and for bright objects, like we looked at rotating stars and stuff, we can go really big. Bright means less than V of 16. So that's not so relevant here. The important thing though is that you have balanced time coverage. It was a supernova survey with rolling cadence. And to get rid of asteroids, it had observations separated by hours. So the asteroid moves off your object, and then you tend to watch the same object for like a week or two. So you have good day sampling, then you come back again in a month and years. It ran for 6 years. So this is like a discovery light curve or post-discovery light curve. Okay, people noticed there was a supernova here, but they can actually track it all the way down going back. So it's good time coverage. And then it's a little slow, all right? And it's a 1 meter telescope, but as Matthew has said or will say, we have tons of observations, at least 100, okay? And you can stack them, okay? And this is Subaru HSC, and this is 100 stacked observations with LSQ, and this is what you get from the legacy server 2 years ago. And you can see stuff here that is not in legacy, but is in HSC. So for some of the places where we have, say, 200 to 500 observations, we hit the systematic limit after you get stack 100 visits. But if we have 500 visits, then we have 5 intervals, so we can do variability, okay, down to 23, even 24. So that's coming, that'll be useful for LSST. Okay, this just proves to you that you can stack stuff. This is an Arlery star, pulsating star on sort of a half-day time scale. At distance 140 kiloparsecs and a magnitude of 21.4 mean magnitude. Okay, so the observations look terrible, right? The error bar is about 0.15 magnitudes. Okay, but we have like 150 observations. So if you median and you look in phase bends, this is a phase folded light curve as a function of period during the oscillation. You can see that you're dead on the profile. So, and you didn't see this, but this is what the sky looks like in our Lyra. There's all sorts of lumps and stuff in our galactic halo. Indeed is not isotropic. Okay. So what I want to focus on the rest is for how do we use this for AGN studies, preparing for LSST. This is what I just said beforehand. Just a couple characteristics. The telescope is in Chile, so the sweet spot straight up ahead is -20 in declination, right here. Okay. And so that's where we have the best coverage. And the way that strategy worked, the exposure time was kept fixed. So as you go up or down, the air mass increases. So eventually our sensitivity down here is not as good. But overall, it's pretty good because we have one filter and the observations are longer than ZTF. If you take standard ZTF, not the force stuff, you can go sort of magnitude a lot deeper. And I'll show you examples where we hit GNR of 22 and we think things are correct. All right. And because we have a 6-year baseline, if AGN varied by 0.1 magnitude per year, and you put in a random walk, over 6 years, you might expect something 2.2 magnitude-ish, and even bad LSQ photometry, all its outliers can handle that level of precision. So we can work pretty faint, okay? And we have several thousand degrees with lots of observations, which is good for testing and making training sets, okay? So here's current AGN survey, which I'm now going to match and just show you if things work or not. Goes to V of 21.5, 22. There are millions of objects potentially, so we have to go machine learning. And this is relevant to like Dimitri's talk. It's quite similar, okay? And Paulo Sanches is the person who did this. And we took the Alurse broker random forest basically, and it's a balanced random forest because you don't have equal numbers of classes. That's important. And we put in lots of variability features, some of which you've seen before, some of which I threw in. We're looking for long-term variability. Gaia proper motions are there, Y's colors W1, W2, and delve extended, not extended, and some other features are there, as well as, for example, instrumental features such as what fraction of the light curve came from a given chip, because some of our chips are absolutely horrible. And I think the random forest sees if that chip is on there, just throws it away. So, but the main thing that you might think, okay, so now you made a color selected usual sample. Yes, that's kind of true, but it's a nested random forest. The first thing that random forest decides, is this a variable object or a non-variable object? And only variable objects pass this cut. So it is a variability based survey. And if you just made it like near infrared selected sample, it works pretty well. but I forgot the exact numbers, but if you're gonna get killed by false positives, okay? So the variability is adding something to you. It makes you less complete, okay? But it gives you a very clean sample. So after we run all this, we put in high quality cuts, then we have sort of 1.6 million objects. And if we loosen stuff up, we can go up to 5 million objects. And I'm gonna show you that this is probably 90% pure. This might be 50, 60% pure, okay? But it picks up some other stuff, all right? So because it goes so deep, that was related to my question this morning, we don't actually know how things are working because there is no good survey that goes that deep yet. Foremost is coming, okay? If I take milliquaz or EFEDS, deep Rosita survey, I'm getting sort of 70% match rates, which means at least 70% pure, okay? I think it's better than that. And the key thing for this group here is, interestingly, if I match all these guys and see who's in what sample, there are objects, a fair number that are missing from each other. So these are all different selection techniques, and they're saying objects that are nominally all AGN, but somehow they're being missed. Okay, so here's an example of comparing to ground truth. I can compare, P means the pure sample high quality, okay? And to compare with milliquaz, that's what it looks like, all right? There are not many sources here because milliquaz dies low latitudes, but interesting, you see all the patterns of the surveys that go into milliquaz. So we're going deeper than the surveys. Here's a confusion matrix, okay? I think maybe Demetra, other people showed. AGNs, we were seeing recover at sort of 93% level, and maybe you're not so impressed here, 83%, 66%, but if you read carefully, these are all periodic sources that even a human has trouble telling apart. So these are periodic stars and binaries, which can look quite similar. We could do a better job of that, but we didn't worry about that. The main thing that's important is getting rid of non-variable galaxies, okay? Because a galaxy, especially with bad telescope like Lucia Quest, and changing seeing will appear variable because it has a fixed aperture and the thing changes. So you have to get rid of all of those. There's a huge background, and it seems to work, all right? And this is what the catalog surface density looks like. When there's good time sampling, we're up to like 140 plus objects per square degree. And then down here where the air mass is large and there was a push to look at more equatorial sources because that's where our telescope follow-up was. We're down to 40, 50, 60, but that's still pretty decent. It's nowhere near the thousands of objects that Neil will give you, but it's pretty good for an optical survey. So then let's just do comparison to EFEDS, which is a deep Rosita survey. It's one of the largest areas we got covered. There were 18,600 sort of X-ray objects, okay? And I took a subset area, which was well covered by LSQ, but I only went to declination 5 degrees. So out of those 18,600, 9,000 are in the LSQ source catalog, or which is Pan stars in this case. So these are the other 9,000 that are not detected, are just too faint to even be in Pan stars. So don't even bother with those. So there are X-ray sources which are too faint, optical, which LSST might get, but we can't with this telescope. So again, we have different selection techniques and instruments finding different kinds of things. All right, of these 9,000, 7,000 are classified as variable, non-galaxy objects. And of these guys, okay, these are the variables. The classifier says 6,700 are AGN, okay? And if I put a tight quality cut, then it drops down to 5,200. So is that good or bad? Okay, 5,200 divided by 18,600 X-ray sources is only 28%. But that's actually not so bad for an optical survey, but that's what we have to confront with LSST and have to think about, okay? The objects that match to LSQ that are bright enough to see, are basically all classified as non-variable galaxies. So the classifier decided, I can't say this guy's variable and it just says it's a galaxy. It doesn't confuse it with stars, okay? Now, the cool thing is adding DESI that came out since then, all right? And the advantage is that EFEDS is an X-ray survey, but it's not, as we're gonna see, it's not complete either. So Rosita, I match Rosita to DESI, okay? Out of the 18,600 objects, 12,000 are found inside DESI. What does that mean? It means that DESI's targeting algorithm didn't pick up all the AGN either, even though the DESI target surface density is like 200 to 300 per square degree. So they're AGN that sneak past DESI, okay? And of those, okay, DESI says 81% are QSOs and 19% are galaxies, and then only 17 out of the 12,000 are stars, so forget about the stars. So what are these galaxies? It's not a QSO, but it's got X-ray emissions, so I guess it's a QSO. But that's the kind of thing we have to think about. Then if I take
2 minutes.
2 minutes, okay, yep. Here's a high quality one. There is 9,000 sources. Okay, of the 93% of them are classified match and DESI, and 97% are QSO. So that's pretty high purity. Okay, so the main thing is I think it's actually doing quite well. And if we match all LSQ targets against all DESI targets, the pure ones, then we have like 290,000, of which 96,000 DESI says are QSO. So I think we have a pretty good survey. And then I just wanted to, what they look like, magnitude distribution, peaks at sort of 21, 22 as we expected. Redshifts, okay, it's good. It's peaking at redshift 1, not what you get from optical surveys, which used to go between 2 and 3. So we're seeing red and AGN for sure. They're all pretty low redshift. Luminosities, we only see bright guys, okay? And the pink is the stuff that was classified as a non-variable galaxy, so we're missing all of those. So not a surprise, and here's a column, sort of 10 to 21-ish. You can't see very obscured objects with optical surveys. And then I'm gonna run over 1 second. Finally, Neil gave me his catalogs. I took them and matched them, okay? So Neil had his W-wide CDFS South, he had 400,000 objects, I only found 284. That's good and bad, you're not impressed, but that means a density of 61 per square degree, which is not great, but not unreasonable for an optical survey. Just tells you how much better the X-rays are. And if I loosen up the cuts, then I get 4 of 36. This one's more interesting. There are 367 objects. Yeah, there. Okay, so we can find stuff, but if I go through, let me just show you the characteristics. They're all 10 to minus 14 centimeters per second in the batches, and they're all bright objects, so we're not finding anything that surprises you, okay? The good cool thing is, here's a plot of the number of observations, and this is sort of, I forget, 40, 50, okay? But there are lots of objects, especially in the way south, which have 1,000 to 2,000 observations, so that should be useful, and I'll stop in a second. Then just here's showing you how LSQ fills in the data. Here's SDSS, and here's ZTF, and here's stars with only a few points and LSQs in the middle, and the error bars are between SDSS and ZTF. And Colin and Weijang and student Margarita have a project to assemble a big database of these. And yeah, if you're after binaries, this is again where the LSQ data would fit in. This is probably not a binary, it's a random selection, okay? Yeah, whatever. And I think I'll just stop there. The cool thing that's coming, as was mentioned, the foremost survey is gonna get started up on the telescope in October-ish. And right, this is Lucia Quest target. So 1.2 million objects will have spectra taken from these. And these are other variability ZTF-based selection. This is from Gaia Quasars, and this is SED, and they all put together. There's actually a huge overlap, but which is interesting. And that's what it's gonna look like. And this is a Venn diagram showing which technique picked out what. And there are lots of empty corners, so different techniques look out different things. So we will have a large sample of AGN that you can use LST. With DESI, we already have light curves for probably by the time I'm done 500,000 objects to train on with redshifts. And then we're gonna have another million-ish from foremost. I'm gonna stop there. Okay. And we're out of time. So that's what I'm gonna do. All right. And I think that, so I'm gonna do force spectrometry, difference imaging to pull out low luminosity AGN. And then I think we really should think about making some dedicated analysis center or pipeline process their own data, because we're gonna miss not transients, but things that change look on 4 or 5 month timescales. By the time we realize it might be too late. So if we can make our own pipeline, that would be good. So this should be proof of concept that we can use a dumb. This is not sophisticated machine learning, but it works. It's stable. We can do better with transformers, but it's good enough. I'll stop there. Thanks. And if you want access to the data, just ask me.
2 questions, please.
Yeah.
I was very interested in the comparison with this, because on a positive note, and the measure that the DST data, we reach 50% some weakness in cosmos, for instance.
Wow.
And hopefully better when
another business. So
Yeah.
I was brainstorming trying to understand what's the difference, since you have more info.
Yeah.
Probably similar or better baseline.
Right. Yeah.
So maybe it's the depth.
I think it's just the depth, right? The key thing that I skipped over, which I went and said, there are 4,000 objects that are in LSQ that Desi says are AGN, they're not in eRosita. That's like 30%. So eRosita is incomplete. So you have to go quite deep in X-rays also. This is much less deep than your survey. I think you went to 23 or 24.
Yeah.
Yeah, so it takes just a little bit of obscuration work on. I think that's the main thing that happened. And if we could do a better job of extracting the nucleus, that would also help, because the host galaxy is washing these out. That's what's going on.
Last word to Chris.
So I also wanted to follow up on the X-rays, but on the other ones, the ones that were X-ray detected, but were not in things that were flagged as quasars, but were in normal galaxies.
Yeah.
So how much variability data did you have on them? Could you
Yes, I can.
figure out how much the nucleus could have varied?
Yeah, possibly, yeah.
If these are the other side of the changing look,
Right.
so you're just seeing reprocessed variability.
Yeah, I was thinking that, yeah, the classifier wasn't confident enough to say this actually varied, but the data is there and they're like 200 light curve points, so you could test that, yes.
That would be a nice test.
So somebody has to give me a truth table of these are real AGN, and I will go.
If it's got X-rays, it's a real A.
Yep.
That's easy.
But it's pretty clear, host contamination is a big problem. Anything extended usually kills it. So it's hard.
Let's thank Paolo again.
All right.
You can stop sharing. So Matheus sets up, so I mean, one thing with the truth tables, like at some level, just like sanity plots, I think help, I mean, strong deviations from Euclidean are a good sign. Right, and then I think your sky plot, the density could be like 10 times, I mean, I'm thinking the Story Fisher had really tiny pixels, and you have the same number of total objects, right?
Yeah.
So should be able to really,
right,
like, are you finding an excess in the LMC, and things like
well,
that?
yeah, I carefully excise that from the plot because there are stars, you can see the LMC perfectly as a round dot.
Yeah, right. You expect that.
No, yeah, right. Now you can see as a function of declination, galactic latitude, you lose it, so.
So you want me to be muted and no video, right?
Yes, I think you'll find your.
Okay.
Yeah. Okay, great. Neil Brandt will tell us about XMM serves and the drilling test.
Great, thanks. Yeah, so I've been involved with Rubin and with the AGN Science Collaboration for almost 20 years now. It's been a long haul, but it's getting very exciting. I used to have a lot more hair and so on. In any case, I come from the deep survey world, and so I love the deep drilling field, so that's what I'm going to talk about today. I had a significant role, in fact, in selecting 4 of those 5 deep drilling fields years ago. And in recent years, I've been able to pursue work on the deep drilling fields through this XMM Serves X-ray survey that I'll be describing. This has supported the work of a number of excellent Penn State graduate students whose work I want to highlight. And today what I will do is I will briefly review the XMM Serves data products that we have produced. Hopefully some of these can be helpful to you when the Rubin data starts showing up in the very near future. And I will also briefly give highlights of some science results that we've derived. So I'll have to go very quickly through these things. So as I said, I love the deep drilling fields. I'm a very simple person. These are my simple arguments why the deep drilling fields are great. They're big enough to be interesting and challenging, at least for a deep surveys person like me, but they're also not so big that they're completely overwhelming. From this morning, it sounded like the wide fast deep might be rather overwhelming for us. They also have, of course, the best multi-wavelength data in the sky. Certainly the regions we're targeting are. They're going to have the best time domain coverage for all the great variability studies. They're an excellent training set for the wide fast deep. And then, of course, extensive early Rubin data will be coming soon. And to highlight that, this is a plot taken from the SITCOM 005 notice. And you can see here that if the validation observations go as planned, we should have, hundreds of visits. In XMM LSS, we'll have 2,900 visits. So lots of great data should be coming quite soon. So that will be very exciting. So now I'll just talk about some of the things the AGN science collaboration has done. So we have been a leader in this collaboration, whether you appreciate it or not, in actually gathering all of the multi-wavelength data in the deep drilling fields. That makes sense. AGNs are so multi-wavelength that is rather necessary. To begin with, I'll just talk about the Spitzer coverage. So Mark Lacey pioneered extensive Spitzer observations in the deep drilling fields, first via a program called SERVS, which is the Spitzer Extragalactic Representative Volume Survey, and then furthermore with the Deep Drill Survey. These are very impressive infrared surveys. We should be very grateful we'll have those data in the can for when Rubin begins in earnest. Furthermore, then I have led work via a multi-year heritage program on XMM, where we spent 5 million seconds of XMM time getting extensive coverage for XMM LSS, for the Deep Field South, and for LISS-1. We couldn't cover the full 10 square degrees. It took 5 million seconds of XMM time to get coverage of these solid angles, which are quite large, impressively large at the depth we've gone, even if they don't cover the full deep drilling fields. To sort of talk a little bit more about these, well, here is an image. This is rather badly washed out. If we can dim the lights briefly, if that's a possibility, I don't know. Just so this is rather washed out, but there we go, it's better. So you can see there all the X-ray sources. If you carefully search the X-ray image here, we get about 5,242 X-ray sources. These are all published, all available to you. And I believe the vast majority of these are AGNs. And indeed, we give characterizations of these sources so you can select out the ones we're very confident are AGNs. Here is the Chandra Deep Field South. Here we have about 4,000 X-ray sources. That's the moon for comparison, by the way. And in this field, of course, we have the advantage of having the super deep 7 million second Chandra data right in the middle of our panoramic X-ray coverage. So we can use that as kind of an answer key, where we have the very best multi-wavelength data that have ever been gathered in the history of humanity. And we can use that to sort of test how well we're doing over the much wider field, because we gathered similar data in here as for the wide field data, and we can just cross compare and see how we do. And we actually do quite well. And then finally, here's the LISS-1. Again, here we have 2,630 sources. So in terms of breaking things down, well, this plot compares things to Cosmos. And you can see that we have a lot of solid angle. I mean, Cosmos itself is a very impressive survey. And we have a lot more solid angle at similar depths to Cosmos. And so very powerful survey, XMM serves. Here are the source number summary. So for all three XMM serves fields together, we have about 11,900 X-ray point sources. 10,200 of those are AGNs, which we've characterized carefully. You can read the paper for the details. They break down to about 2,800 type 1, about 7,400 non-type 1, and then we do have about 1,250 galaxies and a number of stars as well. Again, publicly available source catalogs are available to all of you in those two papers, which took a lot of work to produce. And then, as Paulo mentioned, the XMM source point source sky density is quite high. We're pushing 1,000 sources per square degree. For comparison, with eROSITA, you get about 170 sources per square degree. So we are considerably deeper than eROSITA with considerably better source positions, which is very important for finding reliable counterparts. This plot here shows the multi-wavelength sky coverage. All of these little shapes in here are the various multi-wavelength regions. The surge regions are the regions we targeted. Those are the very best prime regions that have the very best multi-wavelength data in the deep drilling fields. So those are the fields we targeted at highest priority. We got the best things we could in those fields, the surge regions, which are also very similar to the video regions. This table here shows all the multi-wavelength data. I don't expect you to read this all right now, but briefly then, we have utilized those extensive multi-wavelength data as part of this XMM SIRS project. It always has been a multi-wavelength endeavor. We have performed tractor-based photometry, get mass aperture photometry across bands to let us do good photometric redshifts. We've derived photometric redshifts. We've also performed spectral energy distribution fitting, and I'll talk about some of those data products. So here is tractor photometry based photometric redshift. So we use optical data, the video data, the Spitzer data, all with matched aperture photometry from tractor to derive photometric redshifts. We can typically get photometric redshifts to within sort of 3 to 5%, although there inevitably are outliers. And in total, we have given photometric redshifts for something like 2.8 million sources. We don't just do the AGNs, we do all the galaxies as well. Okay, so there's 2.8 million photometric redshifts available to you quite straightforwardly. This plot here just shows sort of spectroscopic completeness, where if you look at the spectroscopic redshifts and then combine the spectroscopic redshifts with the photometric redshifts for the deep field south and for XMM LSS, we can get up to sort of 70% of the sources having spectroscopic or high quality photometric redshifts already. And we plan in the near future to try to improve that. I am quite heavily involved, for example, in the Moons project, and we've taken all of our AGNs and put them in for targeting by moons. We've also encouraged the PFS people and the foremost people to target them as well. So we hope to generate large numbers of spectroscopic redshifts, coming out of this. The photometric redshifts allow optimal targeting with those large spectrographs. So the spectra should be coming along hopefully in the near future. This shows sort of redshift distributions. You can see we span fairly wide ranges of redshifts. And another important point goes to this SED fitting. So Fan Zhao has done a huge amount of work doing SED fitting for 2.8 million sources, running all the way from the X-ray to the far infrared. Okay, we have uniformly extracted and then fit SEDs using the Segal code. The Segal code can natively incorporate the X-ray data. That helps a great deal in breaking degeneracies between galaxy emission and AGN emission. Okay, and then we use the SED fitting to perform source classification into galaxies and AGNs and bursting and quenching galaxies and so on. And we also then utilize the SED fitting to measure host galaxy properties. And as I said before, we can then compare our SED fitting over our wide field region and compare it to the region of the Chandra Deep Field South, which is only 1/35 as large, but has much, much better data still. Okay, and we can look and see how we did. And here's how we do on stellar mass. Here's who we're doing star formation rate, and we do quite well, even with the wide field data and recovering good stellar masses and star formation rates. That's going to be very helpful for people who want to study host galaxies in the deep drilling fields. And this is all available on Zenodo as a huge set of files, which you can access and hopefully use. We also have then gone beyond sort of X-ray and SED AGN selection. We have also done radio-based AGN selection in the deep drilling fields using the ATLAS and the VLA and the MIGHTY surveys. And here we utilize things like radio excess. This plot here shows sources with large radio excesses compared to their infrared emission. We also utilize radio morphology, looking for jet structures and so on. We utilize radio spectral index. And as is known from other fields, we have recovered a large population of radio AGNs that are largely disjoint from the X-ray AGNs and the mid-infrared AGNs. These are, again, the rapidly accreting systems. These are the systems in sort of jet mode or maintenance mode. A variety of names are used for them. They're a largely disjoint population. They're host galaxy dominated through the optical, so they're not going to be spectacular for Rubin, but it's very good to know that they're there. Okay, so you have a large number of those. We found about 6,766 of those. Okay, so that's some of the data products that we can give you. And again, all of these are available at the XMM Serve Survey website. This is the link for the website. Sometimes we will pass you off to Zenodo, like here the data products were so large we didn't want to host them ourselves. We got special permission from Zenodo. The data dump this massive thing. It's bigger than their normal file size limit, but they took it in the end. And so anyway, there's lots of things available to you here. And again, just to quickly summarize, the things that we can give you are general X-ray, infrared, and radio AGN catalogs in the deep drilling fields, derivation and fitting of millions of infrared to X-ray spectral energy distributions for the AGNs and the galaxies, samples of exceptional objects. I'll talk about some of these in the next few slides, such as dogs, dwarf galaxy AGNs, highly X-ray obscured AGNs, highly variable AGNs. We have samples of all those things available. And we have also recently performed precise measurements of average supermassive black hole accretion rates, and also this conditional probability distribution that relates to the effective Eddington ratio of the stellar mass and redshift. And this is another very good way to build your own universe, like we heard about from the earlier talk today. So we have all those things available for you on the website. I encourage you to use them and feel free to ask us questions. I've been a bit surprised that we haven't gotten more emails asking us about these things, because I think they could be a great utility to people. Okay, so I probably just have a few minutes left. How am I doing? So 3 minutes. 3 minutes. Okay, yeah. So I'm going to wrap up here. So we have also, of course, done all this in the context of wanting to execute some exciting science studies. So I have just sort of one slide summaries, each one corresponding to a paper. This is a recently published paper by Bojan Zhang et al. He has done a nice study looking at the star formation properties of the radio AGNs that he did a lot of work selecting. Of course, there have been lots of studies of the star formation properties of the X-ray AGNs by many authors, Montrichus et al., Cristello et al., and others. And, we wanted to look at the properties of the radio AGNs. And what you find is that the star forming fraction of radio AGNs evolves strongly with redshift and also has a clear stellar mass dependence, a -1. And interestingly, as you go out to higher redshift, by the time you approach redshift 2 or so, the star forming fraction of radio AGNs approaches the general galaxy population, unlike what is the case in the nearby universe. Although if you control for the stellar mass trend, it actually is fairly comparable at all redshifts. We've also looked at the main sequence offset, the radioluminosity dependence, and so on. See this paper for more details. We've also recently done selection of a large sample of very interesting dust-obscured galaxies. This is work that was led by Jibo Yu and my group. Of course, these are systems that have very large ratios of the 24 micron to R band fluxes, systems that live in this quadrant of this diagram. He selected 3,738 dust-obscured galaxies and then used all the multi-wavelength data, all the SED fitting to study these objects in detail. And among those, we find about 350 AGNs based on a combination of the X-ray emission as well as the SEDs. These are often X-ray obscured systems, as you might expect. And they show similar AGN fractions as matched galaxy populations, which has implications for the relevance of dogs in the overall merger-driven galaxy supermassive black hole coevolution framework. See that paper for more details. But there are useful constraints there on the role of dust-obscured galaxies and how they fit into all of those things. So that can be of use to you. And these sources, again, tend to be very faint in the optical, but quite bright out in the sort of near and mid-infrared. And so we aim to target many of these with moons. Moons will just kill on these things. And so we're very excited about that. We've also have studied dwarf galaxy AGNs. Again, I don't have a lot of time to talk about this, but Fan Zhao has done a nice X-ray selection of dwarf galaxy AGNs. He characterized them in detail, look at the AGN fraction extending down to very low stellar masses and so on. And then here are the results of our own version of grow your own universe type thing, where here again, we combine the illustrious TNG and that conditional probability distribution we've derived from the X-ray surveys, including XMM serves. And by doing that, you can derive many interesting things. We can set interesting constraints upon the overall roles of accretion and mergers to supermassive black hole growth in the universe. Bottom line, accretion wins. And except down perhaps in the very nearby universe, where most likely even down there, accretion also wins, although the mergers contributed about a 30% level down at low redshift. See the paper for more details on that. We can also, predict the buildup of the overall supermassive black hole mass function over cosmic time. You see it freezing out here at a redshift of 1. Where is the black hole mass in the universe versus cosmic time. And because illustrious TNG, of course, carries along the galaxies, we can also look at relations between black hole mass and galaxy stellar mass. And we have interesting predictions there. So there's that. And again, Gordon getting impatient with me. So we've done a lot of other cool things. We've looked at extremely X-ray variable AGNs. We looked at photometrically selected quasars. See these 2 papers for interesting results there. And I will just end by presenting a few future prospects. So again, there are a huge number of complementary multi-wavelength surveys that are ongoing in the deep drilling fields. It should be very exciting. This top row shows lots of great spectroscopic surveys that we're excited about, again, and are providing AGN targets to in many cases. Of course, Euclid, Roman, in the sub-millimeter and millimeter, hopefully LMT Toltec, and then in the radio. So lots of great multi-wavelength data coming. And of course, I will raise this issue that we have done a pretty good job on the XMM surge regions, on the prime multi-wavelength regions, but there are challenges for the full 10 square degrees of Cosmos, let alone for the full 20 square degrees of Euclid Deep Field South, where things are much more challenging still. The multi-wavelength side coverage, again, we targeted the very best areas, but the multi-wavelength coverage falls apart pretty rapidly once you go outside those very best areas. There are some things, of course, there is now this nice Euclid selection in 2 of the deep drilling fields. That's good progress for Chandra Deep Field South and for Euclid Deep Field South. but one would like to utilize all the multi-wavelength data much better. So that's all I have to say on that. And the final thing I will do is I will just advertise that I also have, in my spare time, produced a sort of a YouTube course on an observational overview of AGN. Some of you may have seen this. I don't know. I encourage students to check this out. It's 10 lectures, 15.5 hours, 640 slides. It's all publicly available for your use. It can be very helpful for new graduate students that want to learn about AGNs and undergraduate students. It should be pretty up to date, and feedback on this is welcome as well. Thank you.
Questions? Yeah, thanks, Neil. I was wondering concerning this population of radio AGN without X-ray detection.
Yes.
How confident are you of their X-ray quietness? And how do they compare with the radio loud and radio bright AGN they have in the Walton universe, which was studied in terms of X-ray to radio luminosity rate?
Yeah, okay. So a whole bunch of questions there, maybe given to me one at a time. So how confident am I of their X-ray quietness? Well, they're X-ray quiet at the level of our survey. Now, what I can also tell you is that, again, as I mentioned, we do have the advantage of having a 7 billion second Chandra survey sitting down in there. So we can look to see, are they also X-ray quiet at that level? Many of them are. For details, see the paper. But many of them are quite X-ray quiet, especially given their radioluminosities. And this is what you would expect. These are the lurgs. These are the lurgs in contrast to the hergs. If you live in radio galaxy world, you live in radio galaxy world, so that's not a thing. Okay, well, these are the lurgs. These are the lurgs. These are the systems where quite likely you've moved over to a radiatively inefficient accretion mode.
Right.
So a lot of your power comes out in kinetic, not so much in radiation.
But do we see them also in the local universe?
Yes. Yeah, lurgs are well studied. This is a well-studied thing among radio galaxy people.
They do have X-ray.
Well, they do it at a very low level. Yeah, they do it at a very low level, but you take it, you can study a lurg at a redshift of 0.01 and get X-ray emission, sure. Put it out a redshift of 2, it's considerably harder, even with a 7 million second Chandra observation, it's very hard. These are very faint. And this isn't new. I mean, I knew this back in 2001. This was well known from the Hubble Deep Field North. We had a very bright radio galaxy right in the bottom corner of the Hubble Deep Field North, very radio bright. We could barely detect it even with 1 million seconds of Chandra time. It's only when we went to 2 million seconds we got it. So yeah, many of them are very X-ray faint. For the reason I just said, and that's true even at a 7 million second Chandra level, over a small area. Yeah, you had a couple other questions. Maybe I answered. Chris. Yeah.
Oddly, I was asking a very similar sort of question.
Yeah.
So I was very interested in these non-X-ray detected but radio detected. Is the radio obviously extended? Is it coming down?
Yeah, for some of them, yeah. So
to be a compact steady jet, and I would expect that to track the X-rays just as a kind of basic zeroth order X-ray emission.
Yes, right. So we have radio surveys from Atlas, from VLA, and from MITE. Okay, they're not the sharpest angular resolution you could ever have, but they're not too bad. VLA is not too bad. So yes, some of them, and it's, I don't know. I could look at the numbers. I have it on this. It's like 10-15% do have radio extent. Some of them have beautiful extended radio jets, as you would expect. The majority of them do not. The majority of them are point light. And this is what you would expect given studies of local lurgs. You look at local lurgs and but they're not that.
Are these, do you think these are X-ray absorbed or are they?
No, they're why are they X-ray faint? It's because they have entered a radiatively inefficient accretion mode.
Well, I was thinking of things like the Cessna's galaxy where it's X-ray faint because it's very high density.
Right, yeah, so, okay, I can't say for every single one.
Yeah.
But what I can say is for the ones, and we have a decent number in the Chandra Deep Field South itself. I mean, there we would detect the Sanches galaxy to redshift 4.
Right.
Because it's so amazingly deep.
Yeah.
So, it's very hard to hide it because if you put it down into a high redshift like that, the X-rays are very penetrating. I can't remember if the Sanches galaxy is completely impenetrable, but I think you can get through if you go up to 20-30 keV to the Sanches galaxy. What's that?
Reflection limit.
It's reflection dominated, but there's a big reflection lump up there. So I don't think the answer in general is obscuration. And I think the answer in general is that, again, it's accretion mode. And this is very much as expected. Again, there's a whole literature on LURBs.
Yeah.
Okay.
They are also, possibly in that if you put, a VLAX spine type of jet and randomize it, put it on some of these simulations, do it across cosmic time, you overpredict the number of Fermi sources by a factor of 1,000.
Yeah, I know this claim, yes. Okay, I have to dig into that.
Yeah,
Yes,
so
okay.
there's something funny going on down there, I think that's really interesting.
Well, it could just be evolution. I think that could be evolution. And that's something where we can work on.
Yeah.
If we get some spare time, would be to look at the evolution of these populations over cosmic time. It's not something that has been our main focus. Again, there's a whole paper, so if you want to see all of our results, I mean, if I know you, this is what you would care about the most, that would make it more.
All right, well, people have other questions for me, I'll post them and I'll forward them to all. So thank you.
Do this.
All right, so Maria is going to talk about searching for supermassive black hole binaries.
That's stable enough.
Thanks. Yeah. First of all, thanks to Matthew for and everyone in the organizing committee for organizing this great meeting. I'm going to talk about quasars with periodic variability and the search for supermassive black hole binaries. Eden already gave you an introduction, but I'll repeat a bit of that. So we know that every massive galaxy has a supermassive black hole, and we know that galaxies merge. So we naturally expect galaxies that will have two supermassive black holes. And we also know that galaxies typically have a lot of gas. That gas is very important because it will end up at the central region of the post-merger galaxy. It can accrete to the black holes and provide the bright electromagnetic signatures that allow us to search for these systems. Now, when we get to small separations, the most promising method to search for these systems is to find quasars that have periodic brightness variations. So why quasars? We think that at least some of the quasars are activated by galaxy mergers. So that makes them very good hosts for having two supermassive black holes. And why periodic variability? Again, I would argue that this is fairly intuitive. We have like an orbiting binary periodically perturbing its environment. But this is also something we see over and over in hydrodynamical simulations. So what we see when we put two black holes in a gaseous disk is that the binary initially acts as a propeller. It expels the gas from the central region outwards, so it creates a cavity of low density material. But this is not completely devoid of gas. We have a lot of dynamic interaction between the orbiting binary and the circumbinary disk. And the broad conclusion from these simulations is that binaries produce bright quasar-like luminosity that is periodically modulated. Now, the exact mechanisms that produce periodicity depend on these features that we see in these circumbinary disks. So we have two main mechanisms that can produce periodicity. One is that we have periodic mass transfer from the disk to the black holes. So when we have relatively low mass ratio binaries, the variability is dominated from these streams here that go into the cavity and hit the black holes. And we see, if we take like the periodogram of the accretion rate, we see spikes at the orbital period of the binary. Now, if we have a relatively high mass ratio binary, so the two black holes have very similar masses, we also see the formation of a hotspot at the edge of the circumbinary disk. And in that case, this is what is dominating the periodicity. So as this hotspot moves around, we get spikes at a few times the orbital period of the binary. The other mechanism that can produce periodic variability is related to these mini disks. So we have gas that gets bound to the individual black holes and moves with the black holes. And if we have a relatively low mass binary and the orbit is not too far from a John, then the variability is dominated by the Doppler boost of the secondary supermassive black hole. So the secondary is the one that is moving closer to the edge of the cavity, and it's the one that is pulling the material inwards, so it has the brighter mini disk. And it's also the one that is moving faster. So in that case, we see periodicity at the orbital period of the binary. And if we have a circular binary, this is a very smooth sinusoidal periodicity. If we have eccentric, that changes a bit. And also the amplitude depends on properties of the binary, like the mass ratio, the velocity of the secondary, the inclination of the source, and so on. Now, in the last 10 years, we had a lot of developments in this field because we had data from large time domain surveys, and we have big samples of AGN light curves that allowed us to systematically search for periodicity. And this is a compilation of past, current, and of course, LSST, which is already working now. So analyzing all these samples of quasar periodicity, we have about 250 candidates. I think Matthew said 1,000 a few minutes ago, but it's of order a few hundred. So it depends on which ones you count as candidates. So these are just some examples of the 5 systematic searches in the big samples of AGN. There's also one very recent from Gaia that I didn't add here that adds another 100 and something candidates. But the problem here is that these are candidates for being quasars with periodicity, because finding periodicity, I don't have to convince this audience, is very hard when we are looking at quasars. And I'll just go through the challenges and hopefully what we can do about this. So one of the challenges is that we are looking at systems that have very long periods of a few years, and we cannot see repetitions of the periodicity many times in the data. So this is just an example from this recent ZTF study where they looked at about, I think, 200,000 ZTF light curves. And initially they detected about 127 candidates only looking at the ZTF data. And then they added additional data from Catalina, PTF, and what other survey was available. And they managed to exclude most of the systems because the periodicity was not persistent in the earlier data. Now, this is going to be a challenge for the longer period binaries. Again, even if we add additional data, whatever we have, probably we won't see that many cycles. And this is a really big problem because the long period binaries are the ones that are more common. Now, another issue is that we typically have a very high false positive rate. And this is because in the limit of a few cycles, we cannot differentiate very easily the stochastic noise from the periodicity. So what we did recently with Jakob Robnik, who is a graduate student at Berkeley, is we designed a, let's say, noise agnostic way to quantify the statistical significance of the periodicity. So instead of assuming the specific noise model and doing simulations to find the false alarm probability, we take the periodic profile, we perturb it to make it non-periodic but still oscillatory. And whatever is picked up by that template is by default a false positive. So that gives us a way to determine the null distribution without assuming anything about the noise. So we used that to reevaluate the significance of the candidates that I had found in PTF. And what I'm showing here is the base factors with the periodic profile. So you can see that we would find very high base factors if we said periodic versus dumb random walk. But we can do the same thing with the null signal template, the non-periodic profile. So the base factor of the null template versus dumb random walk, and you can see that it can produce very, very high base factors. And we did the same exercise with simulations of dumb random walk, but we don't see that we don't get these very high base factors. So that's an indication that the dumb random walk model that we have been using to assess the statistical significance of periodicity is somewhat limited and can introduce these false detections. So Ethan tomorrow will tell you more about how we are further developing this model to apply it to LSST data and also some work with the ZTF data. So another problem is that I think is less appreciated than the false positive rate is that we also have a very low true positive rate. So typically when we search for periodicity, we are mostly sensitive to the sinusoidal periodicity. But if we look at the simulations, more commonly we get something that deviates from the sinusoidal periodicity. So this is, for example, sawtooth from hydrodynamical simulations, but even if we have like eccentric binaries, that can change very much from sinusoids. So with Meg, who is an undergrad at Columbia, we decided to test how many of these signals we could detect with the Carroll periodogram, which is one of the basic tools we use to detect periodicity. So we injected periodic signals, sinusoids, and sawtooths on top of noise, and then we did the statistical analysis that was very similar to what I did in PDF 10 years ago. So we see, as expected, that we start to find more and more signals as the SNR increases. And we also, it's much easier to find short period binaries or short period periodicity compared to the long period one. And the other thing is if we compare sinusoids to sawtooths, we see a dramatic decrease on how many things we can detect. So if we look at the sawtooth, we find less than 10% of the real signals. So this is a problem. So far we are at the situation that we have many candidates. It's very hard to find and confirm them, but binaries also produce all sorts of other signatures. And in this review we wrote with Dan Dourado, we compiled all these different signatures that one can look for. And one idea is that you can look for convergence of evidence. You can look at the different potential signatures, and if one of the candidates shows more than one or more than two, then you start to build the confidence. So if they have jets, and the base of the jet is moving with the binary, that will also distort the jet. So we will have some wiggle jets. If they have broad line regions and that moves with the binary, like Dragana was telling us about Marta's candidate, it can also show Doppler shifts in the emission lines. We can have the photometric center move if we have very precise astrometry, and of course we can have synergies with gravitational waves. Now, the problem is that if you look at each one of these signatures individually, they're very hard to distinguish them from standard quasar variability. As part of this review, we also put together a catalog of binary candidates. It's mostly in the appendix of this paper. And I cleaned it up a few months ago to share it with the binary follow-up task force. So far we have tables that have all the quasars that show periodicity, all the systematic searches, and we also have some additional, some candidates that were found individually. We keep updating this spreadsheet, and we also welcome, if we missed some, to send us an email to put it in the catalog. And this is just maybe Matthew recognized that this is from his 2015 paper, and the green is like from Vincent Fustul's recent work where they looked at additional data and say some of them remain periodic. So we're very open to feedback from you guys on what we need moving forward. For the last 1 minute, I guess, I will talk about synergies with pulsar timing arrays. And I'll skip what pulsar timing arrays are and how they work. They are galactic scale detectors that can find gravitational waves. And it was very recently successful in finding the gravitational wave background, which most likely is a population of unresolved binaries. So the next thing we expect to find in the next few years is one individual binary that will be strong and will be detected on top of this background. We detect them very, very early on in their lifetime, a long time before the merger. So they're monochromatic sources and eternal for our human timescales. And there's a lot of potential for multi-messenger science. And the way it can work synergistically with LSST is that first PTAs can find gravitational waves, and then with LSST data, we can help find the host galaxy. Or LSST finds very good candidates, and then we do targeted searches with PTAs, and we find consistent signals. Now, the good news is that we have a really promising common parameter space. So if we look at what we can detect with LSST, which is the blue thing here in terms of total mass and period of the binaries, and what we can detect with gravitational waves, which are the purple shaded regions, 4 different sensitivities of PTAs, you can see that we are getting into a very interesting regime where we can detect more and more of these with both ways. And the next thing, and the last thing that I will mention, is that we can start thinking of how we can combine gravitational wave data and electromagnetic data. Not going to go into the details, but of the models that I described, the most promising is the Doppler boost, where we can connect all the parameters of the gravitational wave signal and the electromagnetic signal. And very quickly, I'll just show you some results from simulations where we simulate binaries. We analyze them individually, gravitational waves, and these are constraints in different parameters. We analyze the light curve alone, and then we combine the likelihoods and analyze them in a multi-messenger way. And you can see in all the cases, the multi-messenger parameter constraints are much tighter than the individual analysis. So I'll just stop here. The only thing I want to mention is that I will have some postdoc positions in the fall. So whoever is on the job market, keep an eye for those. Thank you.
So could you put up again the one that does PTA and the binary?
This one?
Yeah, that one. So the fact that you search so many, you and others have searched so many light curves and not seen any good signals. What does that already tell us on this diagram?
Well, this diagram tells us what is the common parameter space, what you could detect.
Yes.
Now, if I go to maybe the more relevant thing is maybe something like this, like what are the signals I could detect if they were there?
Yeah.
And then since I'm not detecting something, reverse engineer it about the emission of the binaries.
Yes.
So I don't have an answer about that, but we are working on that.
Right.
Because as Ethan will tell you tomorrow, we ran this pipeline that Jacob developed in 500,000 of CTF light curves.
Yeah.
And we don't find any evidence for like periodicity. So the next step is to do the theoretical analysis and say, what is the fraction of AGN that could have periodicity? What are the amplitudes, periods, and so on that we could detect and don't detect based on this algorithm?
So is CTF already telling you it's less than 1 in a million?
Not necessarily, because I don't know, like, going back and forth between these two, I don't know what's a true positive rate.
Yeah.
With is.
But you could use simulation.
I mean,
Yes, that's the whole.
be fair on this, the problem is that periodicity searches have come from the world of stellar variability, where you're looking for two things that are, you know, primary stars, where it's a very clear Kepler signal.
Yeah.
And we actually haven't done proper methodological work on how do you detect periodicity against more than Brandt walk, a rad noise process properly.
Yes.
And so we don't actually have good techniques for finding these things.
Well, we got some techniques from the expert. Chris has some techniques for exactly that. The party has techniques.
No, because we still don't understand what the background noise process is.
We're starting to understand that.
Yes, we are.
Yes, and the other thing is like the templates we have from the simulations are somewhat limiting, right? We have a lot of work from hydrodynamical simulations, but all of these miss the radiation pressure.
Yeah.
Okay, so I can take this as a template.
If we understood AGN accretion flows on single supermassive, they'd go a lot better with the primary ones.
Yes, fair enough.
Yeah, so, this is somewhat related to the question you just answered, but so of the 250 that you're most familiar with, what percentage would you estimate are false? Matthew stated previously that it was at least 90% and perhaps more. Would you say it's 95%?
Oh, that's a very hard question. I can.
A related question, how much money would you bet that within your sample of 250, at least one of them is actually a real binary?
I wouldn't bet money on that.
Why not?
Because you have a rare source that is less than 1/1,000, you have a high false positive rate, and you have a low true positive rate.
Okay, so your answer is it could well be 100%.
Yes.
Okay.
So I can for sure tell you that we looked at the PDF sample that I produced 10 years ago with this new method, and the answer for this is 100%.
Okay. Yeah, so this could all just be garbage.
It could.
No, it's not garbage.
It's a good attempt.
No. So the thing is, we don't understand then what the false positive mechanism. There's something in the AGN physics which is telling us you're getting modulated behavior over 20-year timescales.
Yep.
What is the physical mechanism that's driving that? So, you know, that's the problem.
And I would also say that there are candidates like PG1302, where we have looked at the optical UV that's also consistent with the multi-wavelength Doppler boost. It keeps doing the oscillatory behavior. It has additional signatures, so it's probably a long game. And LSST may help in the, having the 20 million AGN that maybe we'll find a few that have 3 months periods, right?
Sure.
And then at the end of the survey, we will have so many cycles that all of us will believe.
Then you will believe. Yeah, I appreciate all that. I mean, it is informative that you won't bet any money on it, though.
Yeah, so because of the 3 challenges that I mentioned, right? Not enough cycles, high false positive, low true positive.
Fair enough. That's thank you.
Matthew had some announcements.
Yeah, just before we all disappear off, let me, hang on, I've had a bit